Hi, it's time for another math easy solution. Today I'm going to go over a pretty epic video, and it's going to be on Kepler's laws of planetary motion. And basically I'll be going further into the vector functions, the chapter in my calculus book. Alright, so let's go further. Before we go further, if you don't have time to watch this whole video, as always, you could play this video at a faster speed. Top secret life hack: your brain gets used to faster speed. And there's a link to the video tutorial I made, which I showed the browser extension to increase speed. So I definitely recommend that. And also, you can also download and read the notes in both PDF format, and you could also read the notes in article format on the Hive blockchain. And the links will be in the description below, as well as you could watch a video in parts. And the timestamps of all parts are in the description, so you could skip this intro and so on, just by clicking the timestamp. And also the video sections playlist, I'll upload short clips of this full long video in a giant playlist, and that'll be available also in the link in the description below. Alright, let's continue further. So calculus book reference. Note that I mainly follow along the book Calculus Early Transcendentals, 7th edition by James Stewart. There's a link to that, and also the solution manual for this chapter. And note in my some earlier videos I used the 6th edition there. Alright, now let's quickly just recap on the calculus book chapter, the one I'm currently doing. So the Hive notes and sections playlist for each of this chapter are listed below. There's links to them. Again, all these links will be in the Hive and PDF notes. So there's links to the vector functions playlist, and then the videos I went over already are the first sections of vector functions and space curves. Then I went over derivatives and integrals of vector functions, and then the arc length and curvature. And then these playlist icons, that's the YouTube playlist. These are the Hive notes, and so on. And then I covered motion in space, velocity and acceleration. And actually in that section, they actually did the Kepler's first law, but I'm putting it all together as one video because they had the applied project after that one. So applied project Kepler's laws, and that's the current video. And also note that these links are also on MES links. If you go here, you can see all my links and a whole bunch of links to other stuff as well. So if you click here, you could make this drop down. You could pop this up, so it has them all here. You can pop down, and these are all alphabetical order. So there's vectors in the geometry of space, has all the links to that. And then here's the vector functions I'm covering. So, and this is the current one there. And again, if you click on, for example, here, you get the playlist of, for example, these are the sections playlist. So basically, I put the long video and then I put separate sections, and I'll be doing that for this video as well. All right, let's continue further. So let's take a look at topics to cover. So note that the timestamps will be included in the video description for each topic listed below. So we'll go over Kepler's laws of planetary motion, and then go over proof of Kepler's first law, which basically states a planet revolves around the sun in an ellipse. Yeah, and where the sun is one of the focus on it. Anyways, so applied project Kepler's laws. So this was part of the that earlier section that I just saved it for this video. Is motion in space, velocity and acceleration. And then the second and third laws are part of the applied project. So applied project Kepler's laws, and then solutions to the applied project. Problem 1, prove Kepler's second law. Problem 2, we basically prove Kepler's third law. Problem 3, length of Earth's orbit. And then problem 4, very interesting, a geosynchronous satellite. Basically, it's always in sync with the Earth. It's like a fixed distance away from the equator or something like that. I'll have to deep dive on that. Anyways, let's go further. So Kepler's laws of planetary motion. So we now describe one of the great accomplishments of calculus by showing how the material of this chapter can be used to prove Kepler's laws of planetary motion. So after 20 years of studying the astronomical observations of the Danish astronomer, I think it's pronounced Tycho Brahe, the German mathematician and astronomer Johannes Kepler, born 1571, died 1630, formulated the following 3 laws. So he formulated these just from the data from this guy here, this astronomer. So he basically summed up his findings as these 3 laws, so Kepler's laws. So law 1, a planet revolves around the sun in an elliptical orbit with the sun at one focus. And again, just quickly recap on the focus. An ellipse is just basically defined. You have 2 points like this. The distance from any, basically the distance from this focus 1, this focus 2, like basically if you have a point here, the sum of these distances is going to be constant. And I'll recap on that soon. So, and then the sun's going to be at one of those focus. So law 2, the line joining the sun to a planet sweeps out equal areas in equal times. All right, and yeah, that one is basically if you have if you have the sun here, say the planet's orbiting like here, so and it's moving this way. So after this amount of time, this area is going to be the same as if it was moving across in the same time. So these areas are equal. So this is equal to that one. All right, yeah, that's pretty much how it is. So basically, the line joining the sun to a planet sweeps out equal areas in equal times. So it's the areas are just equaling the same amount of areas being swept through time. So the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. All right, that's quite interesting. We'll get to that in the applied project. Yeah, so basically the period of a revolution. So again, how long it takes a planet to go around the sun. And then it's proportional to the cube of the length of the major axis. So the cube of the major axis is going to be this length like that. And then the cube of it. So basically the square of the period, and then it's proportional to the cube of that major axis. Pretty interesting. So anyways, going further. So in his book Principia Mathematica of 1687, again, Sir Isaac Newton is everywhere. So he was able to show that these three laws, they're just consequences of two of his own laws, basically the second law of motion, that F equals ma law, and the law of universal gravitation. So basically, he can actually derive these, which Johannes Kepler derived just from observations, astronomical, basically astronomical data from this Tycho Brahe guy, and then Newton says, hey, I can actually just prove that just by mathematics. All right, so that's quite fascinating stuff. All right, so let's go further. So proof of Kepler's first law, planet revolves around the sun in an ellipse. So in what follows, we prove Kepler's first law. So law 1, a planet revolves around the sun in an elliptical orbit with the sun at one focus. And now recall from my earlier video where I showed an ellipse is defined as the curve where the sum of distances from any point on the curve to two fixed points called foci, plural, and then focus for a singular, is constant. So you have here, so all these distances right here, this pf1, so this p right there, pf1, pf2, these are just constant. Yeah, so those are always constant. Yeah, so basically any point you go here to here, these are going to be the same lengths when you sum them up. Doesn't matter where you go, even if you go here, from here and all the way here. So you're going to have one long, one short. But it always be constant. You get this curve like that, and there's the sun at one of the focus, and the question is what's its other focus? Right, and then there's the equation x squared, just when it's at the origin. So x squared divided by a squared plus y squared divided by b squared, and then the major axis is over here, and that length is 2a there. So that's a that'd be 2a, like that, and then the minor axis is that thinner one. That's gonna be 2b. Like that. So that's the 2a and 2b. All right, that's an ellipse for you there. And that's at the origins. That's at a0, negative a0, and then 0b, 0, negative b. All right, let's continue further. All right, so since the gravitational force of the sun on a planet is so much larger than the forces exerted by other celestial bodies, we can safely ignore all bodies in the universe except the sun and one planet revolving about it. All right, yeah, so basically this is much stronger than anything else, so we can ignore pretty much most things. But in this case, we're going to ignore everything. So we use a coordinate system with the sun at the origin, and we let r equal, this vector r equals r of t be the position vector of the planet. Yeah, so basically, that's going to be like, if you have make it at the origin, so it's going to be like, this would be the setup there. But anyways, that'd be the origin. Going further, so equally well, r could be the position vector of the moon or a satellite moving around the Earth, or a comet moving around a star. Yeah, so but again, you could use the same the same idea there. Yeah, so for the moon around the Earth, and then the Earth around the sun, you could just use the for those cases, you could use just change the position vector, or just change the origin so that the Earth is the one that's fixed the origin, and so on. All right, but for this case, we have the sun at the origin, and then we let r equals r of t be the position vector of the planet. And here, just for completeness, we made some space here. Let's just draw that out, just for completeness again. So we have the origin like this. Let's say there's the origin, that's the x, y. And then this is the sun right here. This is the sun. Shiny sun like that, and that's at the origin. And then the position vector, let's say we have a planet, it's going to be somewhere around there. Yeah, it's going to be across there. And this is going to be r vector of t. Yeah, so r of t. And there's a planet. So there's the Earth right there. Let's draw the Earth like that. All right. And Antarctica and... Okay, there it is. So that's the Earth. And it's moving around. Yeah. Alrighty, and then, yes, that's pretty interesting there. So anyway, so the velocity vector is v equals the derivative of the position vector. So remember, again, where the curve is, this is just going to be, let's just say it's like this. It's moving like this. Yeah, so then that's the curve. This would be the position vector, the velocity. V is equal to the derivative of that. And the acceleration vector is going to be a equals to... well, r cubed. So it's going to be, let's say that we have a like that. And it's curving inwards there. Or better yet, I think it should be pointing back to the sun there. It's accelerating back in there. Or at least that's where the force is. Yeah, so it's going to be like that. Double prime. And then I'll double check by graphing it maybe later. But anyways, I just want to illustrate some of the terms that we're using. So because the calculus book didn't have that. So anyways, so going further, so yeah, the velocity vector is v equals r prime, and the acceleration vector is a equals to r double prime. So the second derivative of that, or the first derivative of the velocity. All right, so yeah, we use the following laws of Newton. So his second law of motion basically states, well, if you have a force vector, put it like this, this is F, like that, the vector equals to, well, let's have a constant mass times acceleration, and acceleration is a vector. Basically, if you have an object like here, and then if you have an object of mass m, is a mass m, and if it accelerates by a, in order for it to accelerate, you need to have an applied force in that direction. So in order for it to accelerate, there needs to be a force applied to this mass in the direction and then where it's accelerating. So that is the second law of motion. All right, and now the law of gravitation basically states that if you have two bodies, you're going to have again force between two masses. So F equals 2. It's going to be it's going to be negative of the gravitational constant times by capital M is basically the bigger mass, call that the sun for in our case, and then lower mass the planet M, and then divided by r cubed. So this is a distance between them cubed, and that's r, and then basically times it by, it's in the direction of the position vector r, like that. And where basically you have, if you have the sun, for example, I'll make a big one right here. So this is M, that's a sun. Let's say you have a lower one, M, that's a planet. This force, and it's going to be negative. So let's say position vectors like this, from the sun to the planet, like that. So then, and then the absolute value is going to be, well, this is r. And also note that r right here, lowercase r, is just going to be, just r without the vector, is the absolute value of that. And then the force is going to be negative. So the force is going to be negative of the direction there. So that's the force of gravity. It's going to be negative. So in other words, it's going to be attracting to it. Yeah, so it depends where you're drawing your position vector from, but they both experience a force inwards. So the sun, the planet is experiencing a force inwards to the sun, and the planet's experiencing a force of basically inwards to it. But it's also it's also much smaller, so it's actually going to be thrown over there and so on. Yeah, so basically, this was accurate. This is going inwards like that. That's the acceleration like that towards inside there. All right, so yeah, so basically like that. And now what I'm going to do is I'm going to go let u be a position vector of in the direction there. So this equals to r, the r vector divided by the absolute value of r, or the length of r, and that just equals to r over r, lowercase r, like that. And this is just basically equals to unit vector. Unit vector, like fix that up, in direction of r. In other words, if you have r like this, let's say that's r, the unit vector is going to be, well, that's going to be like that, u, because you're dividing by its magnitude, so you always get a 1, and then where this length right here is equal to 1. So basically just, yeah, we're just making it a unit 1, so then we're going to have basically a non-1 value multiplied by 1. So we're going to look at this right here, and then basically rearrange it. We're going to get r is equal to, move this r to the other side, and yeah, we're going to just move that over to the other side, and we're going to get a r times it by unit vector, like that. So yes, pretty much what r is, and we're going to replace that here. So we're going to get this right here, F is equal to negative, this is the gravitational constant, times by mass of the sun, or just a bigger planet, and then lower one, M. Yeah, so M is the planet, this is the sun, and it's going to be divided by, well, this is going to be R times U, so then now that cancels out, and we're just going to left with this R squared. And this is U vector, just make it like that. Alright. Alright, now we have this equation, and yeah, basically here's the terms again. So we're, F right here is the gravitational force on the planet, M and capital M are the masses of the planet and the sun, and G is the gravitational constant. So we first show that the planet moves in one plane. So basically it moves in one plane, and then later we'll show it's an ellipse. Like that. It's basically, it doesn't go in 3D like all over the place. It just goes into a flat plane. So by equating the expressions for F and Newton's two laws, we find that, and basically combine these two. So just F right here. So if we have the force on this planet, F equals ma equals to this setup here, right here. So whenever you have a force, you're gonna get the acceleration there. So let's just equate these. So we're gonna have the force is equal to the first law, or the second law, F equals ma, and the gravitational one is going to be equals to negative capital, or first the G, G m lower m divided by r squared, and then this is going to be the U vector like that. Well, actually, before we even get to the U vector, yeah, we'll just use it the normal setup. It goes to this thing, the r cubed, and then r vector like that. Anyways, we'll just follow along it, and then basically what happens, all we do is just cancel m's. That's all we do. So we have acceleration is equal to negative g m over r cubed and then r vector. In other words, the acceleration is parallel to the position vector. As I already showed earlier, it has this basic common sense. Alright, going further, so yeah, so since A is a scalar multiple of R, again, as I just stated, then they are parallel to each other. So yeah, it's parallel, but it's also the reverse direction. So A is equal to the second derivative of R there, but it's going backwards in there. But it's parallel. So again, this position vector, this is parallel to this one. So I'll just leave it like that. So that's parallel to it. And then now going further, thus, by my earlier video on the cross product, if you take the cross product of the position vector r and a, the acceleration, because they're parallel, the cross product is going to be equal to 0. So the cross product, recall from earlier videos, linked to that, and there is this setup right here, the screenshot, or the thumbnail. So the cross product corollary, non-zero vectors a and b are parallel if and only if the cross product is equal to 0. And now keep this in mind, because if the r and cross product with a is 0, well, it's also the 0 vector, because this is a vector. So it's going to be bold like that. And now also, basically, yeah, they're going to be parallel. It's going to be on the same plane as well. All right. Well, actually, not necessarily, because if A and B are just both changing as well, it could be all over the place. But yeah, so basically this is 0. So now what we'll do now, and we're going to show that it's on the same plane. To do that, now we're going to use formula 5 from our earlier video on the differentiation rules for vector functions, and this is using the derivative. So recall this one here is a screenshot from that. And if we have this, we're going to use a derivative. Basically, it's like the multiplication, the product rule set up for normal derivatives. Notice how it's like cross product, you take the derivative, then cross the regular v, and then plus u cross derivative of the v. And the important part about this is because we're going to take, so if we have, for example, if we did a cross product of r and v, we're gonna eventually get an r cross a, which equals 0. So we're going to take the derivative of v, and then we're going to get something where we can cancel. And we'll show you that as I walk you through this. I'm going to make this bigger. So, yeah, so before I write this one right here, we're going to look at, well, we know that r cross a, because they're parallel, equals to 0 vector. So that's this part right here. So it's a 0 vector. And we also know, or we also have, well, we know that the acceleration is equal to the derivative of the velocity vector. And this just equals to, well, d over dt of v vector. Just for to put it all there. And then we also know that v, and then we also know that the velocity is just equal to the derivative of the position vector, which equals to, again, d over dt of the position vector. Just write it out like that format. And that's because we're going to use this setup right here. And we're going to look at, so d over dt of, and then instead of u, we're going to do r cross v vector. So now it's going to start making some sense. So now this is going to be, well, using this rule, the derivative of this first one, derivative of r prime cross with v prime. Yeah, I mean just v. It was v, and then we add, well, r cross with v prime, like that. All right. So now we know that. Well, this one here, r prime, is just this. It's just v. So this is just v equals to v vector. And now we also know that, well, this derivative right here, this just equals to a. Yeah, so then this equals to v cross v plus then r cross a. All right, and we already know that this is 0. This one is 0 because there's a parallel. But we also know that v is parallel to itself, so that's also 0. So then this whole thing is 0. So this equals to 0 plus 0 vector. In other words, we get a 0 vector. All right, so that's a 0 vector. So thus, what this means is, well, so thus now, this is a derivative. So if we take the integral, so thus, r cross v, well, this just equals to, well, we'll take the full integral like this. Yeah, it's going to be just integral of this whole thing there. So it's going to be d over dt. I'm going to put a bracket because we always need a dt at the end for some reason. Anyways, just for notation, d over dt. And then this is going to be a, I'll put this in this bracket like this, r cross v. And then this is going to be dt, like that. So the integral of basically a derivative is going to be just that whole setup inside. Yeah, and where this part here is equal to 0, so basically this equals to the integral of the 0 function, dt. And the 0 one, we're just going to get a constant. Basically the derivative, basically integral of 0 is going to be a constant because the derivative of a constant goes to 0. So this becomes h, like that, where that's just a constant of integration. This equals to constant vector. Yeah, put the constant vector like that. All right, and now the assumption is, just fix that up, constant vector. So basically, we assume that this constant vector is not equal to the 0 vector. That is, r and v are not parallel. Yeah, so basically, because if it was equal to 0, then you're going to have this setup where it's parallel, and you basically have we're going to have vectors like this parallel to each other. And so we're assuming they're not parallel. So, and that makes sense because if we have it orbiting the Earth like that, the velocity vector is going to be tangent to this curve. And yeah, that's not going to be parallel to this. In other words, it's not going further away vertically, like just straight up ahead. It's not going to go just getting bigger and bigger orbit. It's just going tangentially around. All right, so that makes sense. So it's not going to be equal to 0. So this means that the vector r equals r of t is perpendicular to h for all values of t. Because remember, the cross product is like this. The cross product is always perpendicular to the two vectors. So r, the parallel vector, is always going to be perpendicular to h. So the planet always lies in the plane through the origin perpendicular to h. Yeah, so basically what this means is, well, if you have, this is going to be constant h, like that. And let's say the velocity vector is going to be like v, like that. and this is going to be position vector r. So it's always going to be parallel. I mean, it's always going to be on the same plane there. So it lies in the plane through the origin perpendicular at this. That position vector is always going to be like that. So regardless of what the orbit is, it's always going to be on a flat plane. Like that. Because this is always going to be constant. So it's always going to be the same height. Yeah, same height, but also same direction. So it's always going to be pointing the same height, same direction. It's just constant. This is always going to be pointing like that. So in other words, it never changes. So in order for this plane to curve, like in 3D, this would have to go point somewhere else, but it like points somewhere else, but it never points anywhere else. All right, and also this velocity vector, this is just the velocity vector put at the origin, but then this would be tangent to this setup here, something like that. I'll fix this up. It's gonna be like I'll just do. So yeah, basically the curve. It doesn't matter what the curve is. It's gonna be always on the same plane. Anyways, and then this one's actually gonna be like that. The V's. I'll put the V somewhere like this. V is gonna be something like that. This is parallel to this, and that's just gonna be that, like that. All right. I just put it like that for the cross product setup there. Alright, yeah, so thus the orbit of the planet is a plane curve, and here I just fixed that up, made this this velocity vector a bit better. So now to prove Kepler's first law, which again, that the sun is at one of the focus and the planets move in an elliptical orbit or an ellipse. So to do that, to prove Kepler's first law, we rewrite the vector h, the constant vector h, as follows. And before we can do that, let's look at that unit vector again for the position vector. This just equals to this divided by the position vector r divided by the absolute value of r, like that. Which is again, this just equals to again that r. Just normal like that. And again, that's from before when we were doing the gravitation setup here. So there is this one right here, unit vector in direction of r, just the length is 1 there. Alright, so then rearranging, again, we're going to just do that for completeness. So rearranging this, we're going to get, move this over to the other side, so we're going to get r vector is equal to, this is going to be r times it by, this is going to be r times it by the unit vector like that. And I will circle this. And the reason is because we're going to use this other part too. This is one here. So if we have the velocity v, this just equals to the derivative of the position vector. And that equals to, well, derivative of this just equals to, well, derivative of d over dt of this right here. Just throw it in there. Ru vector, like that. Yeah, and this just equals to, let's put it in this format, Ru and then vector, like that. And we're going to use chain rule, because the r changes as well. So we'll do that in a bit. So now we have this. We're going to write this vector h. So h is equal to, remember what h equals to. Let's scroll up all the way here. So h equals to this part here. So r cross v. All right. So r, again, that's here as well, the cross product like that. So h, this just equals to the cross product r cross v, which is always going to be perpendicular to the two vectors there, and they're not parallel. So there it is. And so this is going to be r cross v, where r equals to this ru. So we'll write that in the position vector format. This equals to r cross u. Or actually, even before we do that, notice that this v, this is equals to r prime. So this equals to r cross the derivative of r. Like that, this just equals to now, well, r is going to be r multiplied by u. Like ru. And then cross it with, this is going to be r prime. So this part right here, r prime is just this. Like that. ru derivative. Alright, and now we have all this, we could just, well, take out this, this r, this is a scalar, so we'll just take that out. So this would be ru like that, and then, well, it's going to be cross, what I mean, I just remove the bracket there, it doesn't matter. So now the next one here, now we're going to take this one here using chain rule of this, again, just basic scalar there. This is going to be r, we're going to have an r prime. Actually, we'll do that other one after. Calculus book just does this one. So it has this r multiplied by derivative of the unit vector prime, yeah, so derivative of that, so u prime, plus now the derivative of the r, so r prime, and then unit vector. So again, just using basic chain rule for vector functions like that. Alright, now that we have this set up, now the next one is, next thing we'll do is just using properties of cross product, as we can just multiply this inside as if it was a regular multiplication and addition. And I'll put a link soon to my earlier video on proving this. So, and also taking the constant, the scalar out of there. So this is going to be multiply, this one here becomes multiplied by there. So r times r is going to be r squared. Those are just scalars. And then this is going to be a u cross u prime, like that. And now the next setup is going to be, well, this multiplies over here. We're going to get an r times r prime. And then we're going to have a multiplied by the u cross u prime, I mean u as well by itself. All right, and now this one, these are just parallel vectors. Yeah, it's just vector with itself. This equals to, well, it's the zero vector. So in other words, what we get is we get h is equal to r squared, and then u cross with the derivative of its the position vector, like that. So that's what h equals. And here, yeah, just recall from my earlier videos, link to the Hive notes, and then if you scroll down to the bottom, it has the link to the sections playlist or section specific video of this and the thumbnails. Put them all in that one giant video notes there. And so this is properties of the cross product. So recall the properties of cross product that I used for this setup here. This part right here. So this RU vector cross with these addition, that's just one here. So if you have a vector cross with an addition of two vectors, it just you basically separate them out and do them individually. And likewise, the scalar, you can move it around anywhere. Take it out, move it to the left and right side. It's going to be the same thing. All right, so yeah, pretty fascinating. And this is the same thing here. If you have the A plus B cross C, it's going to be A cross C and so on. But the order matters when you evaluate it. So this doesn't necessarily equal to this. Not necessarily equal to that. So just check that on your own. But anyways, so now we have this. So now what we'll do, there's an r squared. Now notice the A. If you go all the way back to our acceleration, this word right here, there's an r cubed there. But also when we had it in terms of this u, we have an r squared. So we can actually cancel that out. Well, as a force there, but the same thing. We just write it in the unit vector format. Yeah. So basically, what we'll do is I'm going to write here. Then, if we take because the one we just did above, yeah, this one right here. This is we did r cross v. Well, actually, besides the point, we're just going to take now a cross h. This is going to equal to, well, we know what A equals to negative GM, and then it's going to be that R cubed R, but I'm just going to write it in the other format, R squared U vector, like that. And now we're going to do a cross with H, and H is just this whole setup here, R squared, then U cross U prime. All right, so this is going to be a R squared, and now it's going to be a U vector cross with U prime vector, like that. And now this r squared, this is the scalars. We could cancel these out. Again, cancel out just as we do over here, like this part right here. Yeah, just as we do in this one here. Just move the c's around in and out and so on, and yeah, we can cancel those out and so on. So what we have now is, yeah, we're gonna have actually a pretty amazing setup. This is gonna equal to negative GM. Put this like this. G, then capital M, and now we're gonna have a U cross, and now we're gonna have a U cross with U prime, like that. Now this is an amazing setup here. This is actually a familiar one. We did I derived this in an earlier video. This is actually called the vector triple product, and that's because it produces a vector triple product, because you have and then you have three of these. So U cross and then U cross U prime. Yeah, triple product. So there's three of them. So triple, and then you produce a vector, because you're dealing with cross products like that. So yeah, so just quickly recap on the vector triple product from my earlier videos, link to that, and here's the thumbnail again. Click the notes there, scroll to the bottom, you'll see the link to the YouTube video section playlist and this thumbnail, and you will just see this thumbnail. So basically I derived this one here. So A cross, if you have something that's A cross B cross C, what happens is this is the same thing as doing A dot C times it by B, and again, remember, dot product produces a scalar. That's why we can multiply this over there. And then, yes, basically A dot C times B, and then minus A dot B times C. So that's the order there, and the order is just for the minus there. So in other words, what we get is, thus what we have here. So A cross H, this equals to this part right here, negative GM, and then we're gonna have U cross U prime. Well, we take this one, so A cross C. So in other words, we go U dot U prime times it by U. Yeah. So I guess this one's the same one there. A and equals to B there. So U dot C, so U dot U prime. This is going to be put up like this. U dot U prime, and then multiplied by U. And then minus, and now it's going to be A times A dot B times C. So it's going to be U dot, this one here, U, and then times it by U prime. This is going to be now U dot itself, because A and B, and then C is U prime. Like that. Alright, now that we have these, let's start solving these two parts right here. I'm going to call this 1, and then this part I'm going to call this 2. This is 2. So for the first one, we have, again, U dot its derivative. So this one here, what we'll do is I'm going to write, well, since... well, we know that U, this equals to, again, it's just equal to the R vector divided by its magnitude, which is, again, just the R there. And then now if we take the length of this, so the magnitude of U is going to equal to, well, the magnitude of those. That's just equals to, it's a unit vector. So, and this one, the magnitude of that is just, it's already there, the same thing. This cancels, we're just left with 1. So this is, and then this is constant. So since it's constant and equal to 1, yeah, or just because it's constant there, and again, from my earlier video, then the derivative of this, then U dot like this equals to, well, this is perpendicular. This becomes perpendicular. You could write it like this, perpendicular to U. In other words, perpendicular. Perpendicular to it. Yeah, and I'll just draw it out like this. If we have, this is U, and then U prime would be like this. Like that. So this is always perpendicular to it. Alright, yeah, so since it's perpendicular, or basically has that's pi over 2 or 90 degrees, yeah, pi over 2 radians or 90 degrees, then, yeah, so thus, U, and then dot product with its derivative, that's this part right here. That's going to be, again, you recall the geometric equation of the dot product. And I will, so yeah, basically, and I'll show that soon. I'll recap on it from an earlier video. So this equals the magnitude of both these vectors, and then multiplied by cosine the angle between them, and the angle between them is pi over 2. And this pi over 2, that just basically equals 0 then. So this is going to be, yeah, this is going to go to, that equals 0. And again, recall that from my this earlier setup like this. If you have cosine theta, and this is theta, it's going to recall the graph of cosine looks like that. This is pi over 2. I'll draw this a bit better. This is pi over 2, and there's a 0, and there's the 1 there. So at there, this goes to 0, and that is what it happens. And then this whole thing just becomes 0. And it's a scalar because dot product is a scalar, so just 0, not a vector. All right, so let's box this in. And now, all right, and now let's take a look at the second one here. This is U dot U. So for 2, we got, well, U dot U, again, using the geometric equation, we're going to get a u like that, and then yeah, magnitude times it by itself. Yeah, and then times it by cosine the angle between them. Angles between them as well, they're parallel, so that's a 0. So these are just parallel vectors. So then if it's 0, well, that's equals to 1 there. So this equals to, yeah, this equals to, well, u, this is going to be u like that squared and times by 1. So this equals to 1. Yeah, that's it. And then yeah, I'll just put it by times by 1. And then lastly, this becomes, well, this one here is just magnitude of 1. This is 1 squared, just 1. This is equals to 1. All right, so that's what we have. And here I just quickly just moved it over into one line like that. Yeah, so that equals to 1. So now before we plug these inside here, so this one here is going to equal to 0. This one's going to equal to 1. But before we plug those inside, I'm going to quickly recap on how we obtained all these. So recall the geometric equation of the dot product from my earlier video, which thus shows that the dot product of perpendicular vectors is equal to 0. So recall that a dot b, again, there's a link to my earlier video and the notes, and then you can see the thumbnails and the videos, the short clips of the videos here. So a dot b equals to, again, a dot product b, and then is equal to just the components multiplied by each other and sum them up. So a1 times b1 plus a2 times b2 plus a3 times b3. And then that equals 2. Here's the geometric equation. So a, the magnitude of a times magnitude of b, or that's the length of the vectors, times by each other, and then cosine theta, where the angle theta is there between them. All right, and yeah, going further, so and then yeah, then for perpendicular vectors, the angle is going to be pi over 2 radians, or 90 degrees, and then we get this setup here, so that equals to just 0 there. So if it's perpendicular, dot product is going to be equals to 0. All right, so right here, yeah, a dot product of perpendicular vectors equals to a dot b, a magnitude of a times magnitude of b times, yeah, cosine pi over 2 equals 0. And then also now recall from my earlier video that if a vector has a constant magnitude, then its derivative is perpendicular, thus their dot product is 0. And that is from this first part right here. So since we have the unit vector as a constant, has constant magnitude, which is 1, then its derivative is perpendicular, thus the unit vector dot with its derivative is equal to 0. And yeah, essentially what you have is basically you have, if it's constant magnitude like this, and wherever you go along the curve, in other words, you have a sphere or a circle, depending on if you're doing 2D or 3D. Yeah, so you can see it doesn't matter where you go, it's always going to be on it, and the derivative is going to be perpendicular, or basically tangent to the sphere, and that's how it looks like. And you can actually, the proof is actually in right here, and that's basically by taking the derivative of the dot product of r with itself, where r with itself, again, using the geometric interpretation, it's parallel, so then the angles can be 0, so we're going to have a cosine 0 equals to 1. And then basically, then basically we have this RT squared, which is, it's constant, so it's going to be C squared. And that's, again, follows from this part right here. Yeah, this part right here. So if we have two, I mean, this part right here. Yeah, so if we have the angle 0, and then we have u dot u, because it's parallel, you just have it, well, you're just going to have this setup here, u squared. But in our case, it's equal to 1. So, but it's be constant squared. And then the derivative of a square, of a constant, is just 0. So derivative is 0, but you could also find a derivative using the properties of dot product. Again, the same thing as the product rule for normal derivatives. You would take the, and similar to the cross product. So we have the derivative here, dot with r, and then we have plus r dot derivative. And again, that's from the earlier property here, property 4. So dot product, properties dot product right there. So d over dt, and then u dot v equals to u prime dot v plus u dot v prime. So again, just basic product rule. All right. All right. Yeah. So when you have that, you obtain this setup here. But then these are actually the exact same. You can just add this up, so it becomes 2 like this, and that's because of the dot product setup, where you have, again, it's a dot a b1. Doesn't matter if you have b1 in front or backwards, just regular multiplication. So those are the same. Then you could factor out put them as together as a sum. So 2, and then factor out, or just cancel out the 2, just divide by 0 divided by 2, get them all out of there. So we're gonna be left with the derivative r, r prime dot r equals 0, and in other words, that's if it's constant. So if r is constant, derivative is going to be perpendicular because the dot product is 0. So hence we have this. So that brings us full circle. we basically showed that, basically the whole idea of this whole recap and so on is to show that u dot u prime equals 0 because this is constant. And then u dot u equals to 1 because these are parallel. Like that, yeah. And this is equal to 1. And the magnitude is equal to 1 there. So anyway, so let's just plug those inside. So basically this goes to 0. And this goes to 1 there. We just have the u prime there. All right. So let's just plug it all in here. All right. So we're going to get, I'll just put it thus. This is going to be, and then this was a cross h. And then we'll have a negative gm, but then there's a negative there. So this becomes positive, and this, because this one goes to 0 there. So we're just going to be left with a gm and then u prime. Yeah, that's what we have. A cross with h equals to g, the gravitational constant, times mass of the sun, and then times it by u, the derivative of the unit vector. All right, yeah, so that's what we have there. But now, and so, Clarke's book writes this, and so, well, now we have this. We have the acceleration cross with h. So what we want to do now is just to show you what happens when because we can plug this value in. So that's the thing. I'll just box this whole thing actually. All right, because that's important. So and now if we take the derivative d over dt of v cross with h, like that. And the reason we want to do this is so that we could use properties of a cross product to get an acceleration. Because remember, derivative of velocity is equal to acceleration. And we have this, so we could plug that in there and we get something useful. So this just equals to, again, you could write it in this notation. Clarke's book writes it in this, in the v cross h and then prime, like that. And then using the properties of the cross product, this just becomes, again, let's just scroll back up to that. So that's this, yeah, that's this one right here, again, property 5 right here. So basically when you have the derivative of this, it just becomes u prime cross v, then u cross v prime. So again, just same thing as product rule. So let's go back up there. I just want to quickly recap that. Let's go back here. So now this equals to v prime cross h derivative, and then plus, yeah, and then plus right here. Whoops, I'll move this better. Plus v cross with h prime, like that. All right, and now this we have this. So this is v prime. That just equals to acceleration. This is a vector. And now this right here, we have a derivative of h prime, but we know that h is just a constant. It just equals to 1. So then this derivative right here, yeah, this one right here equals 0. This becomes the 0 vector. And this is since, I'll put a, since h is constant. And then, so then the derivative, yeah, and here I just quickly moved it over here to make some space, and I wrote constant vector there. So since h is constant vector, thus we have h prime equals 0. So the derivative of constant just equals to 0, but it's a 0 vector, like that. And then when you cross product with that as zeros, when you basically get a trivial, all values will just go to straight 0. So now that we're left with is, yeah, what we're left with now is we could plug this inside. Now we get a v cross v cross h derivative is equal to a cross h, and we know what a cross h is. That's just this gm this equals to gm and then the derivative of the unit vector u prime, like that. All right, and now integrating both sides of this equation, we get, and I just want to show you the different ways of writing the notation here. So you could just write, for example, d over dt, like this. Put it like this, d over dt, or put a close bracket, v cross h, like that. So you could put it like this, and then dt, and again, that's the same thing. These dt's just cancel. The same thing as writing like this, v cross h, like that, prime dt. And again, the same thing as writing, again, these all just cancel out. You just have left with a d yeah, d v cross h like that, and that equals 2 again on the other side because we're multiplying d on dt on both sides for notation purposes. Yeah, that's all going to be equal to, well, I'm just going to write now this equals to, well, this just becomes the integral of d over that just becomes this right here. Yeah, that's all it becomes. It just becomes v cross h, which equals, again, the integral of gmu prime, because that's what equals to, and then dt, like that. So, alright, yeah, so this just equals to, well, integral of u prime is just u, and then this is just constant gm, so it just equals to gm u, yeah, just u vector, and then we have a constant of integration, so plus c, where, yeah, so this is what it equals to. I'm just going to box this in, where c is just a constant vector, and that's the constant of integration. That's because when you take the derivative, it just gets a 0 vector. Alright, going further, so at this point, it is convenient to choose the coordinate axis so that the standard basis vector k points in a direction h. And remember, the standard basis k, that just points in a z direction. So then the planet moves in the xy plane, and since both v cross h and u are perpendicular to h, the equation above shows that c lies in the xy plane. And basically this equation shows that this right here, because this one's perpendicular to h, this one has to be as well, because this all thing is perpendicular to h as well. And basically, in other words, these are on the same plane, on the xy plane. And now I will illustrate this. So first of all, note that v cross h, so v, I'll put it here, v cross h, this is just a basic cross product. This is perpendicular to both of the vectors that comprise it, so perpendicular to both v and, v and, like this. This is going to be an and h. So for example, if we go all the way up here for the cross product, again, recall that. So a cross b is perpendicular to both a and b like that. So, and we're going to choose, let's say we have h at the z-axis. So let's say we make h vertical like this. So there's h vertical, and that's going to be basically on the z-axis. So I'll draw the z-axis actually. So let's say z. So h is going to be here. And yeah, it's going to be along that, the k variable there. And again, and remember the setup here. I'll draw it here like this. This is k, the standard basis vectors. This is going to be j, and this is going to be I, like that. So for this, like that, and then we're going to have here, this is going to be our y, and this is going to be our x. So remember, I is just the z, the x component, j is the y, and then k is the z, but a unit vector format, so where it's length 1. All right, so we have v cross h. We set up h like this, and then the next setup is, well, let's just take it's perpendicular to v. So let's say we had a v like this. This is the velocity vectors going something like this. Let's say it's in a direction. Let's say it's going like, I'm trying to think of one, like, let's say it's going like this. Okay, that's our velocity v. So then this is perpendicular to each other. So yeah, so v is, v is perpendicular to h, just because it already goes in the same plane. So we already know that, again, from earlier, when we showed that it's all in the same plane. So h equals r cross v, and in other words, it's perpendicular to both the velocity vector and the position vector. So everything's on that plane. Yeah, so for completeness, I'll put a comma. Yeah, so it's perpendicular to both of these, and we have, and h is perpendicular to v vector and r. So, all right, here I just moved it over here, so and put that there. So h is perpendicular to v and r like that. And then, so now we have v cross h is perpendicular to v and h, so it's going to be somewhere like this. Let's say it's going to be something like this. That's going to be, and it's all in the same plane here. Let's say it's somewhere like that. This is going to be our v cross h, like that. And so v cross h, and now this equals to gmu plus c. Well, u is just the, it's going to be, I'm going to draw a dashed line like this. Let's just draw it like that. So this is going to be, let's say our position vector is like r, like that. I'm just drawing it out randomly like that. So that's r. And then the unit vector is also going to be parallel to that. And remember, r is perpendicular to h. So this is going to be u vector, like that. Yeah, so u is on there. So in other words, what we have is, well, we know that v cross h, so it's not only just a vector, a cross product, which is perpendicular to both h and v, but it's also equal to the sum of this, the scalar, gm, times it by u like that. Yeah, because remember, you're taking the integral. So gmu vector plus c. Like that. Alright, so what that means is, well, if this one is going to be on the xy axis, this is xy plane, I mean. And this one is also on it because this number is perpendicular. This one's perpendicular to both of these, so it's, yeah, directly on there. And then this as well. This also, xy plane. Yeah, this is also xy. And then lastly, the c, well, you're going to add these two together. In order for adding these to get in the same xy plane, this also needs to be on it as well. So let's say we had our c like this. Or I'll move the c like here, actually. Actually, let's say this is r, just to make it, see if that will fit. Let's say it's somewhere over here. I'll make the c like this. It's a constant like that. Yeah, let's just say make it like this. So this is going to be our c. Again, it's not the scale, but that's just the idea there. See, so this is also, yeah, this is also a xy plane. So they have to be in order to add them up and get that. So basically, these are all on the xy plane. So what we want to do is we want to just rotate our reference frame so that c, we want to rotate it all the way up to here. So I'll draw this in red. Yeah, it's just because the calculus book doesn't go over this in detail as I'm doing, just because I want to do it just to make much sense there. So now we rotate it. Yeah, so we're going to rotate all the way across so that it lines up with the x1, and we'll illustrate why we're doing that soon. So I'm going to click here. All right, so fascinating stuff. All right, so going further, and I just want to put this right angles like that. And yeah, they're all right angles each other like that. Anyway, so this means that we can choose the x and y axis so that the standard basis vector I, this part right here, lies in the direction of C. So we'll basically line those up, move it across there, as shown in the figure below. And also, again, these are not to scale, and they might be in the wrong position, but they're all in the XY plane. So what this means is, I'll just draw this, and then I'll use the calculus book screenshot. So let's say we have our Z like that, and then we have our X like this. There's our Y like that. So, and let's say we have our H like this. Alright, so this is our H. Alright, and now we're going to shift this over so C is over here. So C is going to be like this. That's our C vector. And then we have our position vector is going to be somewhere like this. That's it, and it has an angle from the origin there, from the x-axis as theta. This is going to be our R, like that. And let's say the curve, it looks like this. So the planet's moving around the sun in a shape like this, like that. Alright, that's the sun. That's the planet moving around it. And let's say the velocity vector is going to be tangent to that, so this is going to be the velocity, which is derivative of the r there, the position vector. And now the u is just going to be like that, the unit vector along there. So it's going to be something like that. All right, and now what I just did quickly was, I deleted my drawing and just replaced it with the screenshot from the calculus book, because again, it's just much nicer looking right here. So there's our h, there's our c along the x, or the standard basis vector I, component there, and there's our angle between C and or X and C, C and R, or the x-axis. So that's the theta, and then there's the curve in this pinkish red thingy, the curve, and there's the u vector is V, and so on. Yeah, so if theta is the angle between C and R, then then the point R, theta are polar coordinates of the planet. So yeah, the polar coordinates are right here, basically R theta at this point right there. So at this point, this is going to be r theta. So there's our polar coordinates. I'll leave it like that. It's pretty nice. All right, so that's our polar coordinates. And now we're going to get to what we basically wanted to do the whole time, is basically obtain and show that this is all governing the equation of an ellipse. So now if we apply the dot product for equation for V cross H, we can, the one right here, So we have this neat little equation. So if we apply the dot product with it, we can obtain a formula involving r and theta. And I'll put it right here with so v cross h with r. So now we have we can basically use a geometric equation and have theta and r and so on. So we can involve both of them. So what we're going to do is I'm going to write r dot and then v cross h like that. Yeah, so we have this. This equals to, well, r dot, and then replace this with our neat little equation, gm u plus c. So we have gm u vector plus c vector, like this. And then this is dot product. We can just use this basic dot product rules and expand that inside. And yeah, basically we can take the dot product inside and add them up, and then I'll show you a link to my earlier video on that if you want to see the proof for that, but it's pretty straightforward. So we're going to get now a gm scalar, let's move it out of there, and then this is going to be times it by, just times it by, now we have r vector dot with the u vector, and then plus, now this one goes in here, then plus the next setup is now as well. So we're going to get a r dot c vector like that. All right, and now recall how r is related to u, because basically this one r is just equal to, well, it's just equals to the magnitude of r, again that's just r without the vector sign, times it by the unit vector like that. That's all it is. And again, we can scroll back up to see that. All right, here I just teleport all the way beginning there, but again it's pretty straightforward. So it gives a unit vector just to be r divided by the magnitude. And then, and then move it over, we get r equals to this setup there. All right, what we have is, and also this one here, we could use the geometric equation of the dot product, so we get the cosine and so on. So this equals to gm, and then we're going to have a r, just the magnitude of it, and then times it by u dot with u. Again, these are parallel vectors, so in other words, it's just going to equal to 1. We did this already, and basically, and also the unit vector length. This is going to be now plus this part here, r times c. That's just going to be, well, the magnitude of r times by the magnitude of c times by cosine and that angle. So now we have that angle. That's the whole idea. We wanted that between c and r. So when we have that, that's what we could write it in this equation. And now this just equals to this part equals to 1. We already solved that earlier above here. So u dot u is just equals to 1 and so on, and we have the geometric equation here just for generic one. So for our c and our r. All right, so we have all this. Yeah, so what we end up getting is capital G M R, and now we have plus, and then just write r and c like this, r c cosine theta, where again we know that r is already the absolute value or the magnitude of r vector, and then c is the same thing. It's the magnitude of the c vector. So cosine like that. Yeah, and I'm just gonna put this down here. Yeah, so we're gonna put that down there. So basically we have r dot with v cross h equals this setup like that. All right, I'm just gonna box this in for now, and then where c is equal to the magnitude of the c vector, and also just for completeness, r is equal to the magnitude of the r vector. And then g and m are just the gravitational constant and the mass of the sun. Alright, and now I quickly just want to recap on my earlier video on the properties of the dot product. And again, I used property 3 right here. So a dot b plus c is just equal to a dot b plus a dot c. And that's what we used over here. Alright, so now that we have this part right here, so we're going to take this, so what we'll have is, alright then, calculus book just writes then, so we have this whole setup there. We're going to have, I'm just going to write this dot there, so r dot, and then v cross h, and what I'll do is I'm going to factor out this r there, so take that out, so this equals to r, and then we're going to have a gm plus c, c cosine theta, like that. So that's what we have here. We just factor that out. Alright, so we have that. Now we're going to take this and move it over to this side and solve for r. So we're going to get r is equal to, r is equal to, basically the magnitude of r, the position of the planet relative to the sun, is going to be equal to its position vector, r dot with the v cross the h, and then I'll divide this by gm plus c cosine theta. Alright, so now the next thing I'm going to do now is calculus book does this. So basically, it factors out this gm at the bottom. So I'm going to factor out 1 over gm. Take that out of there. So what we're going to get now is a r dot v cross h, like that. And now we're going to have a 1 plus, well, we took it out. Yeah, so then we're going to have, well, we're going to have to divide this out here, so gm. So we took it out of there, so we have a deficit there. And then basically we multiply this inside those all cancel out. So what that means is, well, instead of just writing it like this, I'm going to go let E equals to C over GM, like that. Alright, so we'll keep this here, and this is, again, it looks like the eccentricity of an ellipse, which will, basically in polar coordinates. So we'll get to that in a bit. So I'm going to keep this like that, and we're going to replace that in soon, but we'll do that soon. Alright, so now that we have this, and now notice the scalar triple product in the numerator above. So this right here, notice that, which I covered in my earlier video, and again, it's called a scalar, because we have, basically we have this property as well. So there's a link to that, basically the notes, and scroll down, you'll see the thumbnails and links to videos and so on. So A dot B cross C, if you have a bracket there, is the same thing as writing A cross B and then dot C. And it's called a scalar triple product because, well, there's 3 products there, so A dot or cross there. But it's a scalar because you're dot producting a vector, 2 vectors, so you're going to get a scalar. Compare that with the earlier vector triple product, which I covered here. This was all all cross products, so they all gave a vector. And it turns like that. But this one here, we're basically, and again, you could solve it just using basic in the determinate format of cross product like this, etc. Cross that out, cross this out, multiply and subtract and so on. But then everything's going to become a scalar. So instead of vectors, you do the scalar. But the important part is this one. Is all we need to know is this. Let's put this link just for reference. That thumbnail for reference. But this one here. So what we'll do is we're going to change this up so that we have R cross V. And that's important because we already covered that. Because again, if you scroll back up, we already covered R cross V. And yeah, that's all the way above here. So we already know what R cross V is. That's just H. So R cross V, we already solved it earlier, equals to H is a constant vector. All right, so that's quite amazing. So now we can simplify this whole thing, but just by using the scalar triple product properties there, and this evaluate over there like that. So what we get is here. So we're going to take that R dot. So thus R dot, and then we have a V. V cross H equals to R cross V, and then this is going to be dot H, and then we know that this is going to be, well, our H. That equals to H. So then this whole thing becomes H dot H. Alright, yeah, so that's H dot H, and again, we already know that. Just plug in the cosine setup like this setup here. Like all the way back over here. So we're going to get the U dot U, for example, then we just get U, 2 magnitudes like that, and cosine 0 is 1, and then just U squared, the magnitude of it. But again, it's also part of this property right here. So A dot A just equals to the magnitude squared. So this just equals to, this is equal to H, I'm going to put this like this, magnitude like that squared, which equals to H squared. Just put the H like that. Alright, yeah, I moved it over there. I'm just going to box this out. This equals to H squared. And again, just for completeness, where H is equal to the magnitude of H. Like that, magnitude of H vector. And all right, here I just moved things over here, just a bit neater. So now that we have all this, we could throw this all inside here, and also we're going to replace this with E. But also, I'm going to go let's say move it like this. Yeah, so let E equals to this part equals to C over GM, And then what we also happens is, what happens if we move over the C over to the other side, so just divide it out. So we're going to get a 1 over gm is going to be equal to, so that's this part right here. So we have this and this. We want to just simplify it using E instead. Again, E is for the eccentricity of an ellipse as in polar coordinates, as I'll get to. So move the C over to the bottom, we're going to get E over C. Like that. So that's what we have. And now we're going to throw all that all inside. And this part here is just going to be H. This is going to be H squared. Yeah, so we have all that. And it all simplifies. So what we're going to get is the magnitude. So, I'll write so. The magnitude of R, so again, now the vector, the magnitude, is equal to 1 over gm becomes E over C. Like that, times it by, so that becomes E over C. And now this part here is going to be H squared. H squared, then all divided by 1 plus E cosine theta. Yeah, so now look at what we're starting to get. All right, now before we go further, what we're going to do is I'm going to go let D equals 2, so that we basically see and this H squared there. Let's get rid of those. So that we, and the reason is, so we want to make it look like the ellipse. This is the directrix. So this is going to be H squared over C. So throw that inside, we're going to get, so thus, I think finally, R is equal to, this becomes just D. I mean, we have, this becomes ED. So it becomes ED divided by 1 plus E cosine theta. So basically the length from the planet to the sun is equal to E times D divided by 1 plus E cosine theta in polar coordinates. And then this is just an equation of an ellipse. All right, yeah, so that's what we have. And for completeness, I'm just going to write where E is equal to, this is going to be, recall, this is going to be C over gm. And again, number C is the magnitude of that constant vector there. And then gm is the gravitational constant, m is mass of the sun. So again, that's E equals C over gm. And then D is this one here, D equals H squared over, D equals to H squared over C, like that. And here I just moved it over to that side, D equals H squared over C. And again, remember, H is the magnitude of the vector of the, basically of the cross product of R cross with V. So yes, of the planet's position and motion. So fascinating stuff. All right, yeah, so basically now comparing with my earlier video on conic sections, we see that the above equation is the polar equation of a conic section with focus at the origin and eccentricity E. In other words, if we have an ellipse, if E is less than 1 there, and actually is. Yeah, so here's the thumbnail from my earlier videos, link to the notes there. So PF over PL equals to E eccentricity. So basically the distance is constant. The way this is defined using the unified setup there. And then so if you have this right here, and this is going to be less than 1, so E is constant at less than 1, and that's the focus right here. So distance from PF, and then PL is the distance to the directrix. So basically this ratio, this distance, this distance, PF, divide this by, this one here, you're going to get a constant. So instead of doing the focus, the distance between two focus like this and that, where the unified setup uses this in conic sections like this. And then if it's less than 1, we get an ellipse, and depending if it's vertical or horizontal. So here's the one we were looking at, horizontal one, R equals to ED divided by 1 plus or plus or minus E cosine theta. Or you could also have R equals ED divided by 1 plus or minus E sine theta. So we have this plus one here. This is the one we have. And that's this one here. So absolutely fascinating stuff. So, and we know that the orbit of a planet is a closed surface. Yeah, so it's closed so that it's not going to be like, you're not going to cut this conic this way where you have a hyperbola. If you cut it this way, you have a hyperbola and so on. And it's not going to have it, yeah, you're not going to just slice one segment on it. Let's see, how would you, yeah, you're not going to slice something like that. And you get a parabola, I think. How do you get parabola? Yeah, I think a parabola, you slice it like this. Yeah, so you slice it like that, and you get a parabola. The shape's going to be like that. That's a parabola. And then if you get it vertically cut like this, this is going to be a hyperbola. But we know that the planet is a closed curve, so it always comes back to same setup. It's not going to be flying all over the place randomly. It's not going to be going like a parabola or hyperbola going infinitely further away. So we know that the orbit of a planet is a closed surface, and so the conic must be an ellipse. So we just proved Kepler's first law. So this completes a derivation of Kepler's first law, and we will guide you through the derivation of the second and third laws in the applied project below. And the proofs of these three laws show that the methods of this chapter provide a powerful tool for describing some of the laws of nature. Yeah, so again, quite fascinating stuff here. So again, Newton derived this from his laws of the force equals ma, and the law of gravitational force between two objects, and basically that fits Kepler's observational data that he obtained from that other astronomer guy. All right, pretty amazing stuff. All right, now that I covered the first law, now we're going to look at the applied project, and that's going to look at Kepler's laws, but basically solve the law 2 and 3. And again, just to make a note that this first derivation one, this was at the end of that section on motion in space. The velocity and acceleration that I covered in my earlier video, but then I skipped the this first law here, and I made it because I wanted to do that in one video on Kepler's laws. And then the applied project is the project at the end of the calculus book chapter, and this goes over laws 2 and 3. So I wanted to put all in one go, so that's why this one's going to recap pretty much on Kepler's laws, which I already covered at the beginning, but we're going to recap anyways, because it's always a good thing to repeat knowledge. So Johannes Kepler stated the following 3 laws of planetary motion on the basis of massive amounts of data on the positions of the planets at various times. So Kepler's laws. Law 1, a planet revolves around the sun in an elliptical orbit with the sun at one focus. Again, that's one we just derived. Law 2, the line joining the sun to a planet sweeps out equal areas in equal times, and the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. All right, so Kepler formulated these laws because they fitted the astronomical data. He wasn't able to see why they were true or how they were related to each other, but Sir Isaac Newton, in his famous book Principia Mathematica of 1687, showed how to deduce Kepler's 3 laws of motion. Kepler's 3 laws of orbital mechanics from 2 of Newton's own laws, which are the second law of motion and the law of universal gravitation. So earlier in this video, we proved Kepler's first law using the calculus of vector functions. In this project, this applied project, we guide you through the proofs of Kepler's second and third laws and explore some of their consequences. All right, and there's going to be, I think, 4 problems. So problem 1, prove Kepler's second law. So we're asked, basically, it guides us to it. So it says, use the following steps to prove Kepler's second law. The notation is the same as in the proof of the first law. So I'm going to read all the problems here. And again, you could skip to whichever problem you want, and I'll be uploading the sections playlist and so on. But I'll be reading all this and then go over one problem at a time. So the notation is the same as in the proof of the first law. So in particular, use polar coordinates so that r equals to r cosine theta I plus r sine theta j. And we don't need a 3D component because it's all on one plane there. Again, that's just standard polar coordinates. So we're asked to show that h equals to the h vector equals to r squared d theta over dt, and then times it by the k vector there. That's the standard basis vector, the k1. So deduce that r squared d theta over dt equals to h. And then we're stated right here, if a, part C, if a equals to a of t is the area swept out by the radius vector r equals r of t. In the time interval t0 to t, as in the figure below, show that the derivative dA over dt equals to 1/2 r squared d theta over dt. And basically, here is the figure. So basically, it means like this: if you have a time from rt0 to rt, so this area is going to be the same as if you went from, for example, here over to here, if it's the same amount of time. if the t if the same amount of time t, you're gonna have the same area. So they are equal areas in equal times, and that's a second law right here. Use the following steps to prove the second law, which is the line joining the sun to a planet sweeps out equal areas in equal times. So that's the key one. All right. And then part D states, deduce that dA over dt equals 1/2 times h, which equals to constant, because the number h is the constant vector. Now this is the magnitude of it, and it's a constant. In other words, this says that the rate at which a is swept out is constant and proves Kepler's second law. Basically, the area is basically this. It's the same over same time. So as you sweep it, the rate change of the areas is always constant. So after time t, you're going to have the same amount of area as depending. It doesn't matter where you are in orbit. It's always going to sweep out the same area. All right. So now let's take a look at problem 2, or just read it out. So problem 2 states, prove Kepler's third law. So let t be the period of a planet about the sun. That is, t is the time required for it to travel once around its elliptical orbit. So suppose that the lengths of the major and minor axes of the ellipse are 2a and 2b. And it says, part A says, use part D of problem 1 to show that t equals 2 pi a times b divided by h. And then this is part D of problem 1. So use this to deduce this equation for the period of the planet. So part B says, show that h squared over gm equals ed equals b squared over a. All right, and then and then part C says, use parts A and B, so these two, to show that t squared equals 4 pi squared over gm times a cubed, and this proves Kepler's third law. And notice that the proportionality constant 4 pi squared over gm is independent of the planet, so you basically have a constant there. So in other words, the square of the period is equal to, or is proportional to, the cube of the length of the major axis. 2a is the major axis. Basically, this length. That's the major axis. That's a 2a setup there. And let's go back over to that second law. Read it out. So the square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. That's fascinating stuff there. And now let's read out problem 3 and 4. So length of Earth's orbit. So the period of Earth's orbit is approximately 365.25 days. And it says, use this fact and Kepler's third law to find the length of the major axis of the Earth's orbit. So basically, this is the third law right here. This right here. Third law, this t squared equals this setup equals proportional to the cube of the major axis. And then you will need the mass of the sun, m equals 1.99 times 10 to the power of 30 kilograms, and the gravitational constant, g equals 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. All right, and now problem 4. Again, this one's a fascinating problem right here. So geosynchronous satellite. So it's possible to place a satellite into orbit about the Earth so that it remains fixed above a given location on the equator, and we're asked compute the altitude that is needed for such a satellite. So basically, it's going to be placed in orbit. It remains fixed above a location, so it's like above equator. It's always going to be the same distance. And then we're asked to complete that distance. So the Earth's mass is 5.98 times 10 to the power of 24 kilogram. Its radius is 6.37 times 10 to the 6 meters. And this orbit is called the Clarke Geosynchronous orbit after the Arthur C. Clarke. This is the infamous, or the famous, the 2001 Space Odyssey guy. So after Arthur C. Clarke, who first proposed the idea in 1945, and the first such satellite, Syncom 2, was launched in 1963. So this guy here, the guy who wrote the 2001 Space Odyssey, and he's involved a whole lot of other words. I think, actually I was thinking about somebody else, George E. Wells or whatever. But anyways, Arthur C. Clarke, 2001 Space Odyssey, and now he was also doing this setup right here, Clarke Geosynchronous orbit. He got the idea for 1945, and then the first one launched 1963. So fascinating stuff. And now let's take a look at the solutions to the applied project and start off by looking at the solution to problem 1, which was proving Kepler's second law. All right, so I'm just going to read this again and then basically go over parts A, B, C, and D, and so on. So this one states, use the following steps to prove Kepler's second law, which was, again, I just wrote it here for reference. So the line joining the sun to a planet sweeps out equal areas in equal times. Basically, the area that's being swept by the planet, or a line joining the sun to the planet, it's going to be basically the rate change of that is going to be constant. So the notation is the same as in the proof of the first law. In particular, I'll use polar coordinates so that r equals r cosine theta I, then plus r sine theta j. And then basically we're asked first to show this part, show this equation. And then B, we're asked to show this, deduce that we have this over here. And then if A equals to A of t is the area swept out by the radius vector r equals r of t in the time interval t naught to t, as in the figure below, show that this rate change of the area is equal to this. And then deduce that this rate change is constant. So basically here's that area that's being swept across. And deduce that it's constant, and then this says that the rate at which A is swept out is constant and proves Kepler's second law. Alright, so let's take a look at the solution to that. So first I'm going to do is we're going to use these polar coordinates set up. So r equals r cosine theta I plus r sine theta j. So with this notation, so we have with r, r equals 2, and again, this that's the magnitude of r cosine theta. So r vector equals to r magnitude cosine theta I plus, and then this is going to be r sine theta, and then this is going to be j. And again, to recap why we have this set up is if we have just a vector, so we have xy coordinates as x is y, and we're going to change this to polar coordinates. Let's say we have a vector here, and it has coordinates x and y. Basically, that means then is, well, if we drop a perpendicular line like this, then this x point right here, well, I'm going to draw theta, that's our angle theta. And let's say we had our r vector like that. And then, well, we know basically using basic trigonometry, cosine theta is equal to adjacent over hypotenuse, so that's going to be our x over our r, x over the magnitude of r, that's just going to be, well, x over r. Again, just that's just that, x over a magnitude like that. And then we move this over to the other side, and the same thing is going to be equals to r cosine theta. All right, and likewise, this will be the y, then sine theta. Yeah, sine theta is equal to opposite over hypotenuse, y over r. Move this over, and then what we get is y equals to r sine theta. So again, that's this part, that's the j or the y component. This is the I or the x component of the, and that's polar coordinates. All right, and now let's take a look at the solution to part A. So this part initially was just a notation part over here when we're told just using these basic polar coordinates notation. So now part A, we're asked to show that h vector equals r squared d over dt times k standard basis vector there. So what I'm going to do is, this is what we want. And let's go back here. So recall from the proof of law 1 that r cross v equals h, therefore we have, well, I'm just going to write this right here. So this is what we want. I'm just going to put it over here. So we want this right here. Okay, so we want this like that. And I'll just say we have r cross r cross v equals h, like that. All right, and yeah, this is from our earlier proof of law 1. I'm just going to scroll all the way back up to it, and you could see that it should be right over here somewhere. Yeah, this one right here. So remember here we showed that the h vector is that vertical one equals to r cross v. And there's derivation and so on, just equals, and h is a constant vector. So yes, fascinating stuff. Let's go all the way back now. All right, so this is what we have, and now what I'm going to do now is, well, we know that, well, this right here, v, is just equals to, well, r is just a velocity, it's just r prime. So we have h equals to, yeah, this is going to be equal to r cross r prime, like that. So then this is going to equal 2. Well, let's put this all inside. This is actually going to get a giant... I'm going to put it over. We're going to need a lot more space. I'm going to put... Well, actually, I was going to add more space. I think I'll just put it in 2 lines. So I was going to put it in 1 line. But anyways, it's going to be r. And we know what r is. That's just this part right here. So that's what r is. Then we take the derivative of it by component. So r cosine theta I, yeah, this is going to be I vector plus, and then this is going to be r sine theta j vector, like that. And then we're going to do a cross, and then I'll just put it underneath here. And now we'll write it over here, the cross, and we're going to need a lot more space. And basically, we have now this derivative of the position vector. And then remember, it's derivative d over dt. So this is dr over dt. So these are, we're all going to be taking derivative with respect to time. So in other words, and in r, the magnitude or position vector, all functions of time, even the theta too. So as you move across time, the theta changes. So in other words, we're going to use product rule inside here, inside this part right here. That's going to be r prime cosine theta. And then we have to take the derivative of, well, r is going to be constant. Derivative of cosine is going to be negative sine theta. So put the negative there. And now we have to apply chain rules. Derivative of the inside function is going to be, well, d theta over dt, or theta prime, like that. And again, it's all functions of t. So now it's going to be, this is going to be now I. And now the next setup is going to be plus. Yeah, this is going to be plus. Now this component here, we take the derivative. So we're going to have, this is going to be r prime sine theta. And then this is going to be now, yeah, then we're going to have to go plus, and then r, and the derivative of sine is cosine theta. All right, and now we're going to have a, well, then using chain rule, d theta over dt. Again, that's this part here. We're going to try to get this equation. So that's what we're trying to get. All right, now this is going to be bracket like that. This is going to be, yeah, bracket. This is going to be our j component. And this is going to be like that, bracket, like that. All right, and here I quickly just moved this, shrunk and fit it all into one place. So now what we could do is, well, we just use a cross product. So now this equals 2. So we're going to have to write a giant thingy here. So I'm going to put the I component. So put the I component there. Well, actually, instead of writing this first, I want to put it in the center. I'm going to put, so now this is the I component of the other one. I'm going to put that here. I'm trying to make it centered. So r cosine theta minus r sine theta. So that's going to be this part right here, and then d theta. And then times it by d theta dt. And that's going to be now our I, put this in the middle, I vector. And now this part, top part of vector is going to be r cosine. I'll put this nicer, cosine theta. And now the next one's going to be, well, we're going to write this here, r prime sine theta plus r cosine theta d theta over dt. And then move some space there. This is going to be our j. And now this is going to be, well, r sine theta. Yeah, r sine theta like that. And then lastly, well, we also need a k component because remember it's 3D. The k is going to be a cross product is in 3D, so it's going to be 0, has 0 components because it's the position vector is just in a 2D plane on, well, it's just in a plane, like on a flat plane. But again, cross product is 3D, so the z components are 0. So we have it like that. All right, here, just move this over here. So now the next setup is, well, we're using a basic cross product rule. We'll cross this out. So multiply this by this, and then subtract by this by that. That's just basically get a bunch of zeros there. So this equals 2. This is going to equal to, well, I'm going to put the first one's going to be, well, 0. Yeah, 0i. And now the next one is we cross this out, and now we multiply this by this part, and then subtract by this one here. Actually, but it's the reverse direction. But But anyways, it's going to be, and there's zeros everywhere, so you're going to have a 0. So it's going to be minus I0. The reason is because you minus in the middle one. J, and then lastly, the next one is going to be the only one that matters, is you cross out this part. So again, this is why it's perpendicular to both vectors. So now this multiplied by that is going to get r, yeah, let's just multiply that inside r cosine. So we're going to have a r multiplied inside, we're going to have an r prime. Then we're going to have a cosine theta sine theta. And then multiply that, yeah, it's still inside here. Then we're going to have a plus r squared cosine squared theta, and then there's a d theta over dt, like that. All right, so we have this. And now continuing further, I'm going to make it all in one line. Now the next one is going to be subtracted now. Now you subtract it by these two multiplied by each other. So minus, so now minus r times r prime. So it's going to be minus r times r prime, and now we have a sine theta, but now we have a cosine theta, sine theta. Sine. All right, and then just move it over. Now the next one is multiplied by this negative r sine. So we're multiplying by negative, but we're already doing a negative there, so it's going to be, well, positive. Just put a positive there. Yeah, so positive, and now it's going to be r squared sine theta. So r squared sine squared theta, and then times it by d theta over dt, and this is our k component. Like that. All right, and here I just quickly pause the video and move it over here. Yeah, it's better to write it over there. So now what we're going to get is, well, this zeros all just goes away. And now we're going to be left with is, well, this right here, r, and then r cosine sine theta is the same as this one here. So this just cancels with this. So these two are the same. And now we're just left with this setup here. So this equals 2. Well, we could factor this r squared out. So it's going to be r squared. Yeah, so r squared. Now we're going to have a cosine squared theta plus sine squared theta. And then we have a d theta over dt, and this is going to be then multiplied by the k vector, standard basis vector. So what we end up having is, well, and then this one here is just a Pythagorean identity. This just equals to 1. Yeah, so what we get is h. Remember, this whole thing was h, the cross product of this. So we're going to get h vector equals 2, well, r squared d theta over dt times by the k vector. So we could block this out. All right, and here, just fix that up. But now if we look at above, that's this one right here. That's what we were asked to show. So we're asked to show that we want h equals r squared d theta over dt, and then k vector there. So that's what we got. So we got the exact solution. And now also just quickly recall here from my earlier video on the Pythagorean identity, or the Pythagorean trigonometric identities. I'm linked to my earlier notes there. And there's I got this. I didn't make a proper thumbnail. This was a decade, like I think 10 years ago. So I just found one online right here. So a squared plus b squared equals c squared. This is just a Pythagorean theorem of a triangle. So a squared plus b squared equals c squared. And then in here, you just replace it with the sine theta. The definition of sine theta is equal to adjacent over hypotenuse. But in this case, it's 1. So multiplied by hypotenuse is 1. Just becomes sine theta. Same thing as cosine is adjacent over hypotenuse. This one's opposite over hypotenuse. And then where c is a unit circle equals 1, the radius 1. So then basically using Pythagorean theorem, using Pythagorean theorem, we get the Pythagorean identity. So cos squared plus sine squared equals to 1. So that's this part right here. So again, just wanted to include that. All right, and now let's take a look at the solution to part B. And if we go back up to B, basically, so we have, we showed A as this is the H vector, and now we have to deduce that this equals to H right here. So R squared D theta over dt equals H. Basically, the magnitude equals to this. And essentially, the magnitude is that. All right, so what I'll do is, I'm just going to copy this. All right, so let's go back to the solution. So it's pretty straightforward because we know that, well, since H is a constant vector, we could write it as, well, before I write that, I'm going to go, we want this. Or I'll just put it here. Okay, so we want, all right, we want to show that r squared d theta over dt equals h. All right, so we know that, so h is a constant vector, so the h vector is equal to, we're going to put this, the calculus book just writes it as gamma, it's a gamma and then k vector like that. Yeah, so basically it's a constant, so it's going to be just a constant vector, just a constant scalar multiplied by k. It's in that direction of that unit vector, and where I'll put this, whoops, where this one here, where alpha is greater than 0 and is a constant, and I'll actually move it down here so we have some room, is a constant. All right. All right, so thus, yeah, we know that. So thus, if it's a constant, well, it's just going to be the magnitude of it. So that's if it's a constant, and the magnitude of it is also a constant. So thus, what we have is, thus this alpha is equal to the magnitude of this h, and it's a scalar value. All right, so in other words, what we have is we have h vector equals to basically the magnitude h, and this one's just equal to lowercase h, like that, equals to the multiplied by the k vector, because again it's all constant, equals to h k vector, and then, well, we know that from, so we have that, but we also know that, well, we also know this part right here. So we also know h is that, so basically, in other words, this equals to, this is going to be r squared, just r squared like that, d theta over dt k vector. And this is from part A. This is from A, like that. All right, so thus what we have is, well, h is equal to this part right here. So that's what h is. So thus, or I'll say so, yeah, just because we already have a thus there. So we'll have h, the magnitude of the h vector is equal to r squared d theta, and it's just a constant, d theta over dt, like that. And yeah, basically this solves part B there. So this is what we wanted, and that's what we got. So now let's take a look at the solution to part C. So let's scroll back up to part C, what is asked. So if A equals A of t, so the function of t is the area swept out by the radius vector r equals r of t in the time interval t naught to t, as in the figure below. So it goes from t naught all the way to t there. And then show that the rate change of the area dA over dt is equal to 1/2 r squared d theta over dt. In other words, well, this part here is just h, and that's constant. So in other words, that's the Kepler's second law. So it's the equal area that's being swept with time. So the rate change of the area is always constant as you sweep around, as the planet goes around the sun there. All right, so let's take a look at that. What I'm going to do is I'm going to just copy this and paste it, just because it's easier than drawing it myself. So let's draw out a thin sector of the circle to obtain an integral. So we have, this is the integral, this is the area, a of t, and this is r t naught. And actually, before I even get to that, I want to quickly recall from my earlier videos. Yeah, this first one, there's a second link. The second link to the one screenshot below this, on proving the area of a sector of a circle, because we're going to need this equation. So we know that the area of a circle is pi r squared, or pi d squared over 2. But for a sector, so like this segment there, it's actually a equals 1/2 r squared theta, like that. That's the area of a wedge, like that. And again, it's from an earlier video on area of a circle proof, and I proved it like this setup here using this circle equation, and then using a section of it. And then area of a circle revisited, and this one I used definite integrals, this setup, but again, it's the same equation. You can go and watch those videos for the derivations. But basically, the area is equal to 1/2 r squared theta. So now what I'm going to do is I'm going to draw out a thin sector of the circle to obtain an integral. So I'm going to draw out from here to here. So let's say we have up to t there, and I'm going to draw a slightly a thin here. I'm going to call this, let's say we have a theta here from here to here is theta. And I mean, yeah, theta, this is theta naught. Yeah, I'll write theta naught. And then the other angle is from here to here is theta, yeah, just theta. All right. And now let's say we go slightly further, and this is going to be an infinitely small wedge like this, and this is going to be d theta. So it's like infinitely small. Yeah, let's make this a bit better. D theta. All right. And so what that means is, well, now this length right here, from here all the way over across here. So this length is going to be, yeah, this is going to be this one's going to be r equals to the magnitude of the position vector, r like that. Like that. All right. So now we have a wedge. So we have a wedge like this. So what that means is, so this wedge, we know that the equation of it is, we're going to call this dA. So this is going to be this area. I'll call this dA. So dA, yeah, this dA is equal to 1/2. I'll move it all the way across here. Actually, yeah, I'll just put dA like that. All right, so that's dA. So infinitely small, yeah, change in area there, just a small segment there. So now what we'll write is, well, we know that d of A, and it's a function of t, this equals to, using this equation, of the slice there, so 1/2 r squared, and the radius is just going to be r. So this equals to 1/2, or we'll just write magnitude for completeness for now. It's a magnitude of r squared, and then the angle is d theta, so that's the angle, so d theta. So that's infinitely small one, and we're going to set up an integral. And again, this just equals to, well, I'll write it in the other notation, so 1/2 r squared. D theta. All right, so that's what we have. So then that means now the full area, so this area across this time using the integral, so A of t is equal to the integral, so it's going to be, I'll just put this 1/2 out of there. So integral from, this is going to be t naught all the way up to, yeah, up to t, but just so I'll put the theta naught for now, and we'll just change the variables. So theta naught up to theta of, this is going to be r squared d theta. Like that. So that's basically, they take this little thin slicing, again, it could be anywhere, and we just sum it up or integrate it from theta naught all the way to theta. There. Like that. So then this is going to equal to, convert this into the t variables. So this is the same thing as writing integral from 1/2 from t naught, it's again, same location there, t, and now it's going to be r squared. All right, and instead of d theta, we're going to write, well, d theta. It's a rate change of d theta with time, instead of just rate change just with just angle. Rate with time, and then multiply by dt like that. Again, if you multiply it out to cancel out, so we're going to get the exact same thing. So anyways, so that's what we have, how the integral setup looks like. All right, so that's what we have. So thus, by the fundamental theorem of calculus, we have, well, if we have this area is equal to this, and then basically the derivative, dA, so this means that dA over dt is going to equal to the integrand, again, just by the fundamental theorem of calculus. And we have this scalar there, or this constant 1/2. So 1/2 r squared d theta over dt. So this is going to equal to 1/2 r squared d theta over dt. All right, and we're going to just box this in, because this is exactly what we wanted. And you could see that all the way above here. So that's what we actually wanted to solve, and that's pretty much it. This is, yeah, dA over dt equals 1/2 r squared dt over d theta. And now I'm just going to quickly recap on the fundamental theorem of calculus from my earlier videos. All right, so yeah, going over here. So recall from my earlier videos on part 1 and part 2 of the fundamental theorem of calculus. And also before that, to get that, I want to make a check mark here. Okay, now we got the right answer. All right, so recall on my part 1, there's links to all this. There's part 1, part 2, and there's a fundamental theorem of calculus. There's another one. I was just recap. All right. All right, but anyway, so there's a link to the notes there, and there's some screenshots from my calculus book, as I didn't make proper thumbnails way back when. But anyway, so the fundamental theorem of calculus, part 1. So if f is continuous on a and b, closed interval, then the function g is defined by g of x equals to the integral from a to x of f of t dt. where x is between a and b, so where it's defined, and it's continuous on a and b and differentiable on a and b. So that this function is continuous and differentiable. Well, actually, that's if. So if f is, so if you have this and this is differentiable and continuous, it means you can take derivative, then g prime of x equals to f of x. So the derivative equals to just this f of x there. And that's exactly what we had here. So derivative equals to the inside here, the f of x set up there. And then also recall part 2 is a definite integral, basically integral from a to b of fx dx equals to capital F of b minus f of a, and that's basically f is an antiderivative of f, and so on. And that is, in other words, the function derivative of this is equal to this one right here. All right, and now there's the summary right here. Yeah, so here's a quick summary. So fg of x equals to integral from a to x f of t dt, then the derivative is equal to the integrand inside the g of x, and so on. And there's the part 2 there. F is just antiderivative. That's just using the again in the definite form where you evaluate it out. Anyways, so that is that, and that's what we have there. All right, let's take a look now at the solution to part D. So our result from part C can be written in terms of the magnitude of the constant vector h, which we solved in part B. And again, if we scroll all the way back up to here, so we're asked to deduce that dA over dt equals to 1/2 h equals constant. So basically, to show that this derivative is constant. And then again, we can already see that because this is just h, and that's constant. And that's h, so it's constant. So we already solved it. And basically, this says that the rate at which a is swept out is constant and proves Kepler's second law. All right, so let's read that out again. So our result from part C can be written in terms of the magnitude of the constant vector h, which we solved in part B. So we have this right here. So I'm just going to copy this easier. All right, so we have this. This right here equals that. All right, so that's this is from part C, and now this right here is from, well, part B. This equals to h. So r squared, again, that's all the way here. So that's this part right here. So r squared d theta over dt. And that's constant. So what do you know? It's constant. So this just equals to 1/2 h. Yeah, so it's 1/2 h, and this just equals to constant. And yeah, so this constant, and well, since yeah, it's just constant. Yeah, I'll put it down here actually. So that's 1/2 h equals constant. Since I'll put it right here actually. Since h vector, yeah, I mean the h equals to right here. This is going to be like that. Yeah, or actually, better yet, we can move this down. So where h like that is a constant vector. And then this is that. And then we move this over here. And h is equal to the magnitude of this constant vector there. All right, so that's what we have. So this is constant. All right, and that is correct there. That's what we wanted. So we solved part D. And yeah, so that's constant. So this proves Kepler's second law. Basically, the line joining the sun to a planet sweeps out equal areas in equal times. In other words, dA over dt, the area that's being swept, is constant. Yeah, the rate change of the area. So dA over dt, this area is always going to be the same when you go equal time away from this sweeping. So it's going to be exact same. So it's quite an interesting result there. All right, so now let's take a look at the solution to part 2. And this one we're asked, prove Kepler's third law. All right, so let's read this out again, then go over parts A, B, and C. So let t be the period of a planet about the sun. That is, t is the time required for it to travel once around its elliptical orbit. Now suppose that the lengths of the major and minor axes of the ellipse are 2a and 2b. And it says part A, use part D of problem 1 to show that t equals 2 pi ab divided by h. And then part B says show that we have this h squared over gm equals ed equals equals b squared over a. And then part C says use parts A and B to show that t squared equals 4 pi squared over gm times a cubed. And also notice that the proportional constant right here And actually, yeah, it's pronounced proportionality constant. I mean, spelled this one here. So proportionality constant 4 pi squared over gm. It's independent of the planet. Basically, this is the mass of the sun, and this is g is the gravitational constant. So it doesn't matter about the sun there. So it could be considered as a constant there. All right, so since it's independent of the planet, this proves Kepler's third law, basically the square of the period of revolution of a planet. So right here is the square of the period of the planet is proportional to the cube of the length of the major axis of its orbit. And there's the cube right there. So it is basically, yeah, a cube, so proportional. So t squared proportional to a cube there. It's fascinating stuff. Alright, so now let's take a look at the solution to part A. Alright, and then we're asked use part D of problem 1 to show that t equals 2 pi AB over h. And then part D of problem 1 is basically show that this is constant. So dA over dt equals to this setup, and that's equals to constant. And before we get to that, we're given that the supposed lengths of the major and minor axis of the ellipse are 2a and 2b. So let's draw that out first. So if we have an ellipse, let's say we have an ellipse and we just centered about the origin. I'll just make it. Actually, I'll just draw this out using the built-in thingy here on OneNote. So let's say we have an ellipse like this. So it's an ellipse-ish. It's somewhat like an ellipse. So let's say you have an ellipse like that. There's the origin. And then basically the major axis is going to be length, well, the radius a, I mean the point from the origin to the end is a. So then the length of the major axis is 2a. So that's a and a. And this right here is the minor axis. So that's going to be b, and then this bottom one is going to be b. So in other words, it is 2b, minor axis, major axis is 2a. All right, so now we're going to be given use part D of problem 1 to show that the period equals 2 pi AB over h. So we have this right here. All right, so I'm just going to move it here. I'm just going to copy that and paste it right here. So let's say we paste it. All right, so we have this, and again, it just equals to 1/2 h. It's all that matters. So like that, and this is constant. And now I'll just write this out again. So this is constant. Alright, so dA over dt is constant equals to 1/2 h. Alright, so what happens is, so I'll just write since. Alright, since. What we have is now the area, A of t, is going to equal to, well, the integral of the area, dA over dt. Yeah, basically we move this dt over to this other side, so then basically integral of dA, and this equals to, again, is proper notation, 1/2, and now it's going to be h dt. And now this equals to, so what does this equal to? This equals to, it's going to be, well, 1/2, it's going to be just a constant, and then multiplied by, well, integral of h is a constant, so it's a constant, so we just add a t there. So the integral is just going to be ht. And then plus, well, we're going to have a constant of integration. I'm going to call this c. And I'm going to call it c1. So this is just a constant of integration. So this right here is just a constant of integration. So when we integrate, it's constant just because when you take a derivative, it just constant goes to 0. So we can have any constant we want. Like that. All right, so we know that, but we also know, we know that at basically a of 0, a at, well, t equals to 0, this just equals to 0. Because if you look at the area, the setup over here, let's go all the way back here. So this area, if you have the angle 0 and it hasn't gone anywhere, it's just going to be a thin 0 line. Yeah, just a line of 0 area. If it hasn't traversed anything. So that area swept is just 0 at the beginning. So a at t equals 0 is equal to 0. So what we have is a of 0 equals to 0. And this equals to, plug this inside, 1/2, well, 0. This is going to be 0 plus c1. So in other words, the constant of integration is equal to c1 is equal to 0. So that means and a of t is just equals to 1/2 2ht. So that's what this is. And that is what the area is with at time t. All right, so going further, so note that the area A at t equals to capital T, in other words, equals to period, as it does a full revolution, is the area of an ellipse, whose formula is given from my earlier video, and there's a link to the notes, and there's a thumbnail. So basically, the area of ellipse is equal to pi times b times a, where a is this axis there, the major axis point there, and this is b is the minor axis there. So that's the area there, and I proved it over there, and I compared that with a circle pi r squared. Again, ellipse is just a special kind of circle where it's the a and b are equals to radius, like that. So that's why you get this pi r squared. It's actually, ellipse is just pi a times b. So a circle is actually a special case of ellipse. You can consider that. So that's pretty fascinating. So what that means is, well, we know that a ellipse, I'm just going to put this in completeness, ellipse, equals to pi times a times b, all right? Thus, that the area at t equals to capital T, where this is the period, all right, so that's period. So in other words, it makes a full revolution. So it goes basically a full revolution, so we get a full ellipse. That is when t is equals to the period, and so on. So what that means is this is going to equal to, well, we know that, well, first I'm going to write this out. We know that it's going to be this a over t, so 1/2 ht, but then we put a capital T there. So this equals to 1/2 h capital T, and now this equals to pi times a times b. And again, where a and b are this length right here. This is a at a 0, and then this is at b at 0b, like that. All right, so yeah, going back over here, I just moved it in the center there. But anyways, going back here, so what we have here now is we move this over there and solve for t. We get so then we'll get right here, t is equal to this is going to be the 2's on top, so 2, and then divided by, this is going to be divided by h there. Yeah, so we're going to get a 2 pi a b over h. I'll move this a bit in here, like that. I'll move this better and move it right here. All right, so there's a period, and that's what we wanted to solve. All right, now if we go scroll all the way back up, well, we wanted to show it equals to 2 pi a b over h, and that's what we just solved. So there it is. We just solved that. That's check mark. All right, and yeah, now we have that. Let's take a look at the solution to part B, and this one states, well, if we go all the way back up here. So part B, show that h over gm equals ed equals b squared over a. And again, remember, ed is from the equation of the ellipse from part 1. I'm not part 1, from the first law derivation. So recall from the earlier proof of Kepler's first law for the value of ed, which are the eccentricity and directrix of an ellipse in polar coordinates. I'll write that in here. In polar coordinates. Yeah, all right. So that's using the unified conic theorem setup. So this is what we want. I'm going to write this here. So we want here. So we want. So we want to show that we have this setup. Basically, h squared over gm equals ed equals b squared over a. So what I'm going to do now, I'm going to scroll all the way back up and then find the equation of the setup there. I'm going to go all the way back to the first law derivation. So if we go all the way back, and that was before the applied project, so we had this setup. All right, so we have this. I'm gonna just copy this. All right, so we have that, and we already know those values, ed. So we're gonna go all the way back down here and just paste it straight into here. All right, so we have that. So I'm gonna paste this here. All right, this is I'll put it like this. All right, so from this is from law 1. I'll put that like that, law 1. So from law 1 we had this r equals ed plus and then divided by 1 plus e cosine theta, where e equals c over gm and d equals h squared. Well, we could easily solve for ed. That's just we already know what e and d are. So that means so thus ed just equals to, well, c over gm times it by this. We just throw these inside. That's all it is. So yes, that's what we have. So obviously this like that times it by h squared over c. In other words, this cancels, and we're just left with an h squared over gm. All right, so we have this first part. So we got this. Now we got to show that it equals to b over a. All right, and now what's needed, the next step to prove that it equals to b squared over a, the major and minor axis, we have to basically convert this back into the normal ellipse setup. Instead of using the polar ones, we need to use the xy setup like this. And this is from earlier video, so again, it's a recap on that. So the ellipse we are dealing with is just horizontally shifted from the origin, as in the as I illustrated in my earlier video. So there's a link to that, as well as obtaining the values of a and b in terms of E and D. So from my earlier video, here's screenshots from my calculus book. Just neater than my writing there. So recall that if we had this equation, r equals ed divided by 1 plus e cosine theta, and again that's what we derived for the planet around the sun. And then where f is the focal point focus, and that's where the sun is. So I'll just draw the sun there. All right, so that's sun. That's a bright spot. And then the directrix is on the side here. X equals d directrix, and then basically that is the that d part right here. So that's a d there. And then the eccentricity is remember, eccentricity is going to be, well, point on there, pf, and then this is going to be, well, distance p d there, yeah, or pl or pd. I think it's just, I'll write this as, PD, or PLPD, doesn't matter. I'm just going to scroll back up just to recap quickly on ellipses, and that's right over, it's going to be way above. Yeah, it's right here. So I chose the L there, or you could also put D, it doesn't matter, D or PL, etc. So again, that's, and the eccentricity is just the, it has to be constant there, so the point from PF, so this point PF divided by PL. All right, here, just quickly teleport it back here. And again, this could be L and so on, doesn't matter. Anyways, that's just what the E is. All right, so we already have that covered. And then I showed I basically derived this, made it back into the normal ellipse equation setup. And what we end up having is if E is less than 0, we recognize this equation 3 here as equation of an ellipse. In fact, it is the form of this right here is a horizontally shifted one. And this is just horizontally shifted there, all right? So basically x minus h over a squared plus y squared over b squared equals 1, where, and then I already saw this, h equals to negative e squared d divided by 1 over 1 minus e squared, and then a squared equals to e squared d squared over 1 minus e squared all squared, and then b squared is e squared d squared divided by 1 minus e squared. So again, I'm not going to derive these again, so make sure to watch my earlier video on that, and we're going to just use these results, namely this one and this one here. Alright, so now that I've recapped this, so yeah, what we want to do is, again, we want to get ED equals to this setup here, b squared over a squared, and we already know that ED is equal to h squared over gm, so basically relating these, the elliptical orbit of the Earth around the Sun, or the planet, and then with these major and minor axes. And then that's from over here. So what I'll do is, so thus, let's write down these two equations, the ones we want, because there's an ED in both of them. But notice that they're squared. So what we have is a squared is equal to e squared d squared over 1 minus e squared. So keep an eye on the squared, and then squared. Whereas b squared only squares the top part, e squared over d squared, and then the bottom is just 1 minus e squared. So you don't square this one here. Notice this one is squared, and then this one is not squared. The 1 minus e squared is not squared. All right, so that's what we have. So what I'm going to do now is, well, if I take the square root of that, this is going to be just square root both sides. Same thing over on the other side, like that and like that. So what we get is, let's put this like this. So what we get is, we're going to get a squared. Yeah, I mean, a is just going to be like that. And then we have the top ED over, this one squared is going to be 1 minus e power of 2. Whereas b is going to be, well, b equals to e d over square root 1 minus e squared. All right, and again, number is all plus or minus, we just take the plus. as always, because you could have plus or minus for some reason. All right. Anyways, so that's what we have. All right, but what we are actually interested in is actually the ratio. So if we remember here, we want b squared over a squared. So that's what we want. But we know that, well, a squared. I'll just write this here. A squared divided by b. A divided by a squared divided by b squared. Yeah. So what this equals to is, well, we're gonna have this would cancel with this. And then this, only the square is canceled. This one is canceled with this. Because you're just dividing it by it. So we'll just erase all this. And erase, and erase, and erase. All right. So that's what we have. So this is going to be, well, just EDs all cancel. We're going to have a 1 over 1 minus e squared. Okay, yeah, so basically the only thing it has more is just this. This is an extra 2 squared there. So that's what we have there. All right, so what I'm going to do now is I'm going to take this right here and then multiply it inside there. So what we get is an ED equals to A times it by 1 minus E squared. And again, what is that equal to? Well, that's just, well, we know this E squared right here. This right here, 1 minus E squared, well, you could just move it over to this side and then move this, and then flip these around. So then if you flip these around, this would be on top. So we just flip those around. So in other words, we could just have it like that. This is just going to be equals to, and then basically throw that in here, like that. So what we're going to get is A, and now because it's the A minus E squared on the numerator, this is the denominator, we just flip these. This equals to times it by B squared. So we flip these over A squared. All right, so that's just this part right here. Yeah, let's put it like that. And this equals to, well, this cancels with this. And we're just left with a B squared over A. All right, so we solved it. There it is. All right, if I go back up here, we have B squared over A. So now we basically solved everything. H squared over GM equals this right here. H squared equals ED, and then which equals to B squared over A. So let's just write that down. So that's what we solved. We have H squared over gravitational constant times mass of the sun equals to E centricity times by directrix equals to the minor axis squared over the major axis, not squared. All right, so that's what we have. So solves all this. All right, yeah, so now that we have this, I'm gonna put a check mark. Now let's take a look at the next part, and that's solution to part C. So let's just scroll all the way back up to part C. And that's right here. So use parts A and B to show that t squared equals 4 pi squared over gm times a cubed. So use parts A and B and basically use this equation and these equations and then basically solve for t squared in terms of this A there. All right, so what we'll do is, let's just put that in there. So from part A, from A, we get, well, t, remember this one is equal to 2 pi, that's this part here, 2 pi AB over H, 2 pi AB over H. So 2 pi AB over H. And then from B, we just have this part top there, is we have an H squared over GM over, I'll fix this up. GM equals to ED equals to B squared over A. All right, so that we have that. So then what we want to do is get the t squared. So thus, if we square t squared, we're going to get, well, this just becomes all squared. So it becomes 4 pi squared and then a squared, b squared, like that, over h squared. All right, so over h squared. All right, so what that means is, well, look what we have. We have a b squared over an h squared there. So yeah, we have this right here. Yeah, so we have a b squared over h squared. What that means is, well, we could just, we take this h squared, move it over to the bottom, and then, and then move the a over to the top. In other words, what we get is, I'm gonna just yeah, I'll just leave that here. But what I'm gonna do is I'm just gonna write here just for completeness, just for ease of use. So this is a squared times it by b squared over h squared. And also we have this part right here. So that's what we have. And then we also have this is going to be now, well, we have h squared. Oh, I'll just put and. So we have that and h squared over gm equals to b squared over a squared. Over a. So then basically this, move this around, move this down, and move this one up. What we get is a b squared over h squared equals to a over gm. Again, we just move it around like that, basic algebra. All right, and then we can throw this inside there. All right, so we get t squared equals to 4 pi squared a squared, and then multiplied by a over gm. Yeah, so the b is gone. Yeah, a over gm. In other words, we get 4 pi squared over gm, and then this a squared times a is just a cubed. All right, so we solved it. So there it is. So that's quite fascinating. So t squared, yeah, so I'll put this all together. Yeah, so we just have t squared is equal to, so it's proportional to, these constants right here are independent of the planet. That's just gravitational constant. That's the mass of the sun. And pi is just pi, and this 4 is just 4, just squared, times by a cubed. And yeah, so the period of, the square of the period of the planet is proportional to the cube of its major axis of its elliptical orbit. It's fascinating stuff. All right, yeah, so this basically proves Kepler's third law. Notice that the proportionality constant is independent of the planet. And again, we could just go all the way back up here and then just double check it. So there is the problem right here, all the way here. Where's the problem? And that is, yeah, this right here. So t squared equals 4 pi squared over gm times by a cubed. Again, just double check that. All right, let's go back here. Yeah, so that proves Kepler's third law. This proves Kepler's third law. Notice that the proportionality constant is independent of the planet. And the square, basically, here's the third law. The square of the period of revolution of a planet is proportional to the cube of the length of the major axis of its orbit. Again, fascinating stuff. All right, and now that we have that, let's take a look at the solution to problem 3 and look at length of Earth's orbit. So the period of the Earth's orbit is approximately 365.25 days, and we're told to use this fact and Kepler's third law to find the length of the major axis of the Earth's orbit. And you will need the mass of the sun, capital M equals 1.99 times 10 to the power of 30 kilograms. And the gravitational constant, capital G equals 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. Those are the units. All right, so let's take a look at the solution. So from problem 2, and that's basically this part right here. This is the third law, this right here. So what I'll do is I'll just copy this, actually. We're going to need that. I'll just copy that. So from problem 2, and converting the period of t of the Earth to seconds, since the unit Newton, and there's a Wikipedia link, in the gravitational constant has units of kilogram meters per second. In other words, mass times acceleration. And this is just, acceleration is meters, distance divided by seconds. Squared or second per, basically meters per second. And that's how rate of velocity is changing. So that's this Newton right here, and that involves seconds. So, and since we're given this period is in days, we want to convert that to seconds and then throw that in there. And so I'm going to put this right here. So t squared equals to 4 pi squared over gm a squared, and again, m has kilograms, but then now this Newton has seconds. So that's the thing, we need to convert it over there. And what we'll do is, well, t equals 2. I'll also put it right here, actually. Yeah, I'll put it down. I'm gonna put this in a circle. I'm gonna move this around here. So that is our from problem 2. This is law. So that's law 3 from problem 2. All right. And then we know that T is equal to, for the Earth, 365 days, 3.25, so yeah, 365.25 days. Now we need to convert that to seconds. So we know that there's 24 hours in a day, so 24 hours in a day. So then again, we just cancel all the units. So then this would cancel with this. So again, and then we're left with hours. But then there is also 60 minutes. Yeah, 60 minutes. I'll put, yeah, I'll just put 60 minutes in 1 hour. Put an hour like that. And then there's also 60 seconds. Now let's put 60 seconds over 1 minute. 1 minute. So then basically what we end up having is 365.25 times 24 times 60 times 60. And this is actually going to be approximately equals to 3 point, as it's going to be 3.1558 times 10 to the 7 seconds. Or there's a lot of zeros there. In there, that's how long it takes for the Earth to rotate about the sun. So it's period. So that's how many seconds it is. And I'm just gonna box this in actually. All right. So that's what we have, and now we're asked for, again, we want to find the length of Earth's orbit. To find the length of the major axis of Earth's orbit, so how big it is. And that's going to be, well, we just solve for a cube there. So we basically do this, move it over all there. So we would move everything over to the other side. So we get a cubed is equal to, this is going to be, well, we're going to have a t squared times by g m and, yeah, and divided by, but instead of writing t squared, I'm going to write this as actually gm t, change order, and then t squared, and then divide this by 4 pi squared. All right, so that's what we have. Now this is going to be approximately equal, it's actually going to be approximately equal to all those figures there, because those ones aren't exact values. So g is going to be, g is 6.67 times 10 to the negative 11 Newton. So 6.67 times 10 to the negative 11. And this is going to be, what is it? Newtons meters. This is going to be Newton meters squared over kilograms squared. And then, so that's the gravitational constant. And then this is going to be, now mass of the sun is 1.99 times 10 to the 30 kilograms. All right, so just so we know, all the units have to all line up. So this is going to put a bracket like that. And then t squared is going to be what we just solved. So this is going to be 3.1558. And again, I will do a calculation check. So if you plug that in the calculator, you get that. And 3.1558 times 10 to the 7s, like that. And then this is squared. All right, and then divide this all by 4 pi squared. All right, here I just shrunk it all the way inside here. And again, notice the units. We have this newtons. Remember, newtons is going to be is just kilogram mass times acceleration. So it's going to be kg. Yeah, it's going to be kg times by meters per second squared. So in other words, we're going to get this kg, and then there's a kg here, and then that becomes, well, cancels with this kg squared. And then we have a meters squared times meter. We're going to have a meters cubed. And then we have a second squared. This cancels with the second squared there. So again, that's the units. And these other ones are don't have any units. Those are just random constants. All right, related to the circle. Again, whenever you have 4 pi, a circle or ellipse, and so on. So this is going to equal to, roughly, and when you plug this into the calculator, you're going to get 3.34, that's 348 around there, and I'll do a calculation check soon, times 10 to the power of 33, and then now we have the units of meters cubed, like that. And then what that means is, well, we take the cube root of it. So A is going to be, well, the cube root, and that's going to be equals to 1.496 times 10 to the power of 11, like that, meters. And yeah, so we get the cube root gets the meter, so that's the length of the major axis. All right, and yeah, basically now what we get is, well, this is A, but again, notice that and recall that the length of the major axis is actually 2A. So again, if we recall above here, so the major axis is 2A. So that was just from the origin to the end. So yeah, it's actually 2A. So we have to multiply that by 2. So, and again, we're asked to get the length of the major axis. Yeah, so it's not just A. So this is just half, 1/2 major axis. Alright, so thus the length of the major axis of Earth's orbit, that is 2A, is approximately 2.99, so multiply everything by 2, times 10 to the power of 11, which is equal to 2.99 times 10 to the power of 8. And again, when you divide this by 1,000 kilograms, I mean kilometers. So there's 1,000 meters in a kilometer, so divided by 1,000. In other words, divided by 3 zeros, so we get 8 instead of 11. All right, and here's a calculation check. That I did above here. So 365, and again, my OneNote calculator, my OneNote thingy, this Microsoft OneNote has a built-in calculator. So 365.25 times 24 times 60 times 60. So just plug that in, and just all you do is write. Let's go. I mean, we can just erase this and then write space equals space, and it automatically solves it. And again, 3.1, they have 31,557,600, and then we could just use the dots there. So we have dot 3.155, round this up to the 8, and then there's going to be 6 zeros plus 7. Those are the power of 7. Now, or yeah, basically, yeah, that's how many orders of magnitude there is. How many digits there, and then this one right here, 1 over 4 pi squared, that's this whole setup here, times it by 6.67 times 10 to the power of negative 11, times 1.99 times 10 to the power of 30, and then times 3.1558 times 10 to the power of 7, and then all squared. Again, put this in the OneNote calculator, it automatically solves this. Is actually quite remarkable. So there's 3.34840 all the way, and then it says E33. That's just the same thing as writing times 10 to the power of 33. So that's just the exponent 33 there. All right. And yeah, so 3.348, and then that's what we have, 3.348 times 10 to the power of 3, and that's meters cubed. And then we need to take the cube root, and again, you just take the cube root like that, and automatically solves it. Space, that's 1.496, and then times, and then you would have to get, there's E11. That's the same thing as 10 to 11. And then when you multiply by 2, so there is this number, 1.496 times 10 to the power of 11. Times by 2, we get 2.99, and then all the way to the E11. And again, you can just use this. I'll do this just for completeness, and per space, it automatically calculates. Or 2.99 times 10 to the power of 11, and divided by 1,000, you get this setup here, which is what we just did. All right, so that's what we get. So that's fascinating stuff there. All right, now that we have solved problem 3, now let's take a look at the last problem, and that's basically a solution to problem 4, geosynchronous satellite. So it's possible to place a satellite into orbit about the Earth so that it remains fixed above a given location on the equator. So in other words, if you have the Earth right here, and you have a satellite over here, there's the dish and so on, like that. And it's always going to be fixed with it. So as this rotates, this is also moving about it. So you're always seeing it with a telescope. Yeah, exactly the same location always. So it appears to be stationary. So that's fascinating. I'll see if I can find a video after this after this problem. I'll add some other context, as well as this Arthur C. Clarke guy, who's pretty famous here. So yeah, so it's possible to place a satellite into orbit about the Earth so that it remains fixed about a given location on the equator. And now we're asked, compute the altitude that is needed for such a satellite, and the Earth's mass is 5.98 times 10 to the power of 24 kilogram, and its radius is 6.37 times 10 to the 6 meters. All right, and then this orbit is called the Clarke Geosynchronous orbit after Arthur C. Clarke, again, the 2001 Space Odyssey guy, who first proposed the idea in 1945. That's, yeah, I think it's end of World War II there. So the first such satellite, Syncom 2, was launched in July 1963. So he was way ahead of his time. 18 years later, that's when they launched it first there. So fascinating stuff. So solution. So we adapt the equation from problem 2C with the Earth at the center of the system. So instead of the sun, we're doing the Earth just because relative to the distance, this is much closer to the Earth than it is to the sun. So this will be, and the mass is much smaller, so it's going to be going around the Earth as opposed to around the sun. But eventually it's going to go around the sun as Earth goes. All right, so we can adapt the equation for problem 2C with Earth at the center of the system. So T is the period of the satellite's orbit about Earth, and M is the mass of the Earth, and A is the length of the semi-major axis of the satellite's orbit measured from the Earth's center. And again, this is the calculus book calls this semi-major axis. That's just basically the major axis divided by 2. So again, remember the major axis is 2a. That's major axis 2a, and then the semi-major is just a. All right, so that's just a there. All right, so that's what we have. All right, so let's take a look at the problem 2C again. So scroll back up to problem 2C. And that is, well, this is problem 2C again. Again, it's the same equation right here, the period. So we're going to change this up so that, well, we're just going to be looking at the mass of the Earth as opposed to the mass of the sun there. All right, so, and yeah, so I just pasted that there for reference. Oh, and now since we want the satellite to remain fixed about a particular point on the Earth's equator, T, right here, the period of the satellite must coincide with the period of Earth's own rotation. So T is equal to 24 hours, which equals to 86,400 seconds. So basically, yeah, the period of the Earth's spin. Yeah, I mean, the period of the like if you have the Earth right here and you have the satellite, I'll make it like this, something like that. This has to go around the same amount of, that's T, has to go around the same amount of time as Earth's rotating T, so that these have to be equal. So that you're always going to, if you're on here, and as Earth's rotating, you're always looking at this, so it looks stationary, so that's quite fascinating. All right, so it needs to coincide, and we are given that the mass of the Earth is m equals 5.98 times 10 to the power 24 kilograms. So, and also I just want to show this just to complete our work, have completeness of our work. So we have a period as 24 hours. How they get this is basically times it by 60 minutes in an hour, and then times it by, well, 60 seconds in a minute. So basically times 60 squared, and this equals to 86,400 seconds. And I'll do a calculation check soon. So what we have here, well, this is the period that we need to have. So in other words, we need to find the length of the semi-major axis, basically the major axis divided by 2. So we'll solve this. That's going to be, well, the cube root of that. So this is going to be a, which is going to equal to, move everything over to this side. So GM on top, this one's at the bottom. So we'll have a, I'll put this like this, t squared, or actually instead of t squared, put the GMT as we did before. So GMT squared, divide this by, divided by 4 pi squared. And then we're going to do the cube root right here. So in other words, 1 over 3. So you could do that. Or you could also write it like this. You could also write, I think, like this, 3, like that. I'll put both just for completeness. And then this equals to GMT squared divided by 4 pi squared. And then this is 1 over 3, like that. I just wanted to write both just for a mathematical mumbo jumbo. All right, so now this is going to be approximately equal to when we put in the values. So let's put these values all in here. And the top part is going to be, well, we have the G. G is going to be, again, the same thing as before, 6.67. That is this right here. G is 6.67 times 10 to the negative 11 newtons meters per second. Newton meters squared divided by kilogram squared. So 6 6.67. I'll put this nicer. All right, 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. All right, and then this is going to be like that. GM, and then mass of the Earth is 5.98 times 10 to the 24 kilograms. All right, and then we have the last one is going to be, as the period squared, so that's just going to be 86,000. 86,400 second, 86,400 seconds, and then all squared. And then this is going to be, well, put a close bracket, divide this by 4 pi squared, and then this is going to be power of 1 cubed. All right, and now we plug this into the calculator, and then again, all the units they all cancel out. We're going to get the meters as we did over above in problem, in problem 3. So we just get the meters like that, and then number of newtons is kilogram per meters times meters a second squared, and then what we get is kilograms divided by kilogram squared cancels, and we get a meter squared, and then times a meter, so meters cubed. And then the seconds cancels with this second squared. And all we're left with is, meters cubed. And then we get this cube root, so we get meters. So this is going to be approximately equals 2 when you plug in the calculator. This is going to be 4. I'll put the A there. So thus A is the semi-major axis, so 2.3 times 10 to the 7 meters, like that. Like that. All right, so now that we have this, the length of the semi-major axis, or basically major axis divided by 2, let's do a quick calculation check, and then we'll go further. So calculation check, so again, we have this part here, 24 times 60 times 60. Plug that in. This per space equals 86,400. And then over here, this 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 86, 1,400 squared, and then all times it by, that's this part squared, and then all times it by, or divided by 4 pi squared, and then a cube root. And again, you could just use this giant formula and you get the answer. All nice and tidy there. Equals to, 4.2250, and then etc. E7. In other words, 4.23 rounded up, round this 3, and then times 10 to the negative, times 10 to the 7. So again, fascinating stuff. All right, so now going further. So if we assume a circular orbit, the radius of the orbit is A. So again, assuming it's not an ellipse, it's a circle. Just because relative to the Earth, the orbit isn't that much bigger than the Earth. It's still bigger, but not as big. So the radius of, and also for simplicity for this video, I'm pretty sure the actual satellites will be more accurate. So anyways, if we assume a circular orbit, the radius of the Earth, radius of the orbit is A, and since the radius of the Earth is, radius of the Earth is 6.37 times 10 to the power of 6 meters, the required altitude above the Earth's surface for the satellite is, and basically what I'll do, I'm going to draw this out now because it's a circle. And it's a circle, so what I'm going to do, I'm going to try to make it more accurate, just because this is 10 to the 7 is the semi-major axis, in other words, the radius, because we're assuming a circle. And again, just for simplicity's sake, assuming a circle, and also because the Earth is pretty big, and the satellite isn't that far away, I'm assuming. But regardless, I think the actual astronomers would have the satellite at more accurate elliptical orbit. But anyways, what I'm going to do now is I'm going to insert a circle. I'm going to try to make this accurate. All right, so we have that, and I'm going to go right here and try to make this as accurate as possible. So that is a circle. It looks a bit, I'm going to make it a bit more circularly set up. Okay, so it's going to be like this. I'll make it bigger. Anyways, it's not fully round, but I just wanted to make it looks decent enough. So now, and the reason is, this is times 10 to the 7. This is 10 to the 6. So basically 10 times bigger is the semi-major axis. So Earth is going to be something like this. It's going to be pretty small, actually. I'm just gonna draw it a bit. It's not gonna be fully accurate, but there's the Earth. It has radius r. I'll go like this. This has yeah, it has radius r, and now the length, the major axis of the satellite is gonna be like this. This is a like that, and then the satellite's gonna be somewhere here. It's again not the scale, but it's gonna be something like this, and then it goes all the way around. Yeah, so it goes all the way around. And then the period is going to be t has to equal to, well, 24 hours. Yeah, 24 hours. I'll put hours like that. And this Earth is rotating. Yeah, I'll put this, how am I going to do this? Yeah, I'll just move this R out of there. I'll make this a bit bigger just so we can fit this in. So this is going to be our R. And now this is going to be rotating at well, rotating, the Earth's rotating just at 24 hours. So again, that's the Earth's spin. So these have to be equal, and then basically, yeah, that's the to scale, roughly to scale. It's going to be a bit, actually even further out, because this is, it's not going to be 10 lengths. Yeah, it's going to be around 10 lengths. But anyways, I made it like that. And we know the mass of the Earth and so on. So the required altitude is, so we know A. So basically, the required altitude is going to be from here to here. And or I'll make it from here. I'll make it here. So this is going to be, and move this here. So that's going to be the required altitude, and that's going to be a minus the radius. All right. So required altitude is going to be a minus r, which equals 2. And we know what a is. A is above here, 4.23 times 10 to the power negative, times 10 to the power of 7. 4.23 times 10 to the 7 meters, subtracted by the radius of the Earth, 6.37 times 10 to the 6. 6.37 times 10 to the power of 6 meters. And also this is going to be approximate because we're using rounding up numbers and all that. So it's going to be approximately equal to, well, when you plug this into the calculator, you get 3.59 times 10 to the power of 7 meters. All right, so it becomes like that, and then divided by, again, by 1,000. So this is going to be basically divided by 1,000. We're going to get 3.59 times 10 to the power of 4 kilometers. Again, is the standard units right there in metric system. They're basically, yeah, like that. Or this is going to be 3, I'll make this in actual full numbers. So it's basically 4 decimal places. So we're going to get 3, 5, and then we have 9, 0 kilometers. So 35,000 kilometers, 35,900 kilometers altitude. And this is going to be altitude. Yeah, altitude above Earth. All right, just above. I'll say above equator. All right. Let's circle this. All right, and now let's do a quick calculation check. So we have that. So basically, calculation check 4.23 times 10 to the power of 7 is this part right here, minus 6.37 times 10 to the power of 6, and then usable built-in OneNote calculator space. Yeah, equals 3.593 or 3.59, just rounded down, times 10 to the power of 7. There's E7 at 7, and then divided by 1,000, you get kilometers. We just put that in, divided by 1,000. Equals that, and just put a space here like that. All right, here I quickly just added an animation from Wikipedia. So here's an animation, not the scale of a geosynchronous satellite orbiting the Earth. So if I click that over there, I already have it open. So if we just go over here, geosynchronous orbit on Wikipedia, and here's animation, not the scale, showing geosynchronous satellite orbiting the Earth. So there it is. It looks like that, and it's going around it, and as it's basically following along the Earth's rotation, and it's always going to be pointing around this point on the equator there. And but again, we use 24 hours. It's actually Earth's rotation is about 23 hours, 56 minutes, and 4 seconds, and that's one sidereal day there. That's basically yeah, fixed point like that. And if you make it solar day, basically, where accounting for the sun movement, it's going to be, I think you add, you add another minute there. So that's why it's 24 hours there. This is 23 hours, 56 minutes. All right. And then I just want to make a point right here. So over the course of a day, the object's position in the sky may remain still or trace out a path, typically in a figure 8 form, whose precise characteristics depend on the orbit's inclination and eccentricity. Again, that's with the whole ellipse, because we just assumed a circular orbit. So a circular geosynchronous orbit has a constant altitude of 35,786 kilometers, and that's pretty close to ours. We had 35,900. So again, pretty close there. And then next thing I'm going to do is I'm going to click over here. So if I click here, figure 8, the reason it's figure 8 is, again, as Earth's rotating around, you're going to have a shape like that. This is a geosynchronous shape like a figure 8. And again, these are called an analemma. Let's go back up to here. So you also have that for the sun here. So a diagram of an analemma, and here's the pronunciation of it. Let's see this.
Analemma.
Yeah, so that's analemma, all right. And yeah, so this one's diagram of an analemma looking east in the northern hemisphere. The dates of the sun's position are shown. This analemma is calculated for 9 a.m., not photographed. All right, yeah, so here's the dates right there. This would be, I think, this is June 21st. And then this would be, this is December right here. Okay, this is December 22nd. Yeah, so notice how December 22nd, it's at the lowest, and these are 9 a.m. Photos. So the sun's lowest at 9 in the winter, and then it's highest in the summer. And notice that's why it goes up. And then because Earth's moving around and tilting and all that, you're going to have this weird shape like that. All right, and you also have an analemma of the moon, and you could, if you do a search right here, see where it shows up on the moon. So there's analemma of the moon. Apparently, more people have walked on the moon than have captured the analemma. Interesting. So here's analemma of the moon, 2005. So if I go here, this credit Richens, what kind of name is that? All right, that's quite an interesting name there. So anyways, this is July 2005. Yeah, I mean, July 13th, 2005. So you can see right here. So there's a full, a new moon there. It's a hiding, and then you see the crescent. It gets bigger and bigger, and this is going behind the Earth. And you can see that different shape, that's pretty amazing there. And I mean, behind the Earth, I mean, the sun is going to be opposite of this. So as the sun's opposite, you're going to have this refraction and so on as red. More of the red light is showing on there. So it gets bigger. So notice the figure 8. So again, absolutely fascinating stuff. All right, so let's go back over here. All right, so now I'm going to end this video with just some info on Arthur C. Clarke, as again, this guy's everywhere. So according to Wikipedia, first of all, so more info on Arthur C. Clarke. So according to Wikipedia, Hermann Podgnik described both geosynchronous orbits in general in 1929. The first popular literature to mention a geosynchronous orbit was in 1948 by George O. Smith, but Arthur C. Clarke was, he popularized and expanded on the concept in 1945, hence it is sometimes called the Clarke orbit or the Clarke geosynchronous orbit. So there he is with this epic shirt there, and also he has this New York Times magazine walked on the moon there. Interesting. And there's a nice Mac. All right. So I want to just go over some info about this guy. It's pretty fascinating stuff here. Yeah, so Arthur C. Clarke, born on December 16th, 1917, and died on March 19, 2008, is the famous author of the 1968 novel turned movie, 2001 A Space Odyssey. Interestingly, it was written concurrently or at the same time as Stanley Kubrick's film version and published 1 month on June 1968 after the movie was released, which was April 2nd, 1968. I'm not sure the exact day in June, but nonetheless. So here is the cover of the novel there. So 2001 A Space Odyssey, a novel by Arthur C. Clarke, and based on a screenplay by Stanley Kubrick and Arthur C. Clarke. And notice how they're in space here. They got a spacecraft there. And also notice this giant circular thingy there, and that's basically, it creates a centrifugal force to mimic gravity, so you can exist in there while you're basically rotating constantly. So that's quite fascinating there. Now, some interesting info on it. So, the 2001 A Space Odyssey movie features a black monolith, which looks just like the Millennium Hilton Hotel building that stood facing the Twin Towers, and the hotel phone number is you can make it up is 2112-693-2001. So there's a black monolith there, and yeah, so you have the monolith there. There's the monkeys there, or gorillas, and now you have interestingly. So there's the Millennium Hilton Hotel standing right next to the Twin Towers. On 9/11 there, and again, the contact number is 2112-693-2001. Again, it's called Millennium, and we'll get to that naming as well. So again, it looks like just a black monolith there, and then it has 2001 in there. And also, there's actually someone on 9/11. Her name was Tammy Michaels, and she actually called someone and said she was at the Millennium Hotel, and her phone number is 2112-693-2001. So we'll open this up actually. So I posted on Hive blockchain / this is on 3Speak. It's also on YouTube on my other channel, Me as Truth. But I'm going to play this beginning. It's only a few seconds. Let's play this.
Flames are coming out the window. We've been told to stay in our hotel. I'm watching this right in front of me. I don't have to call to tell you. I'm at the Millennium Hotel. My phone number here is 212-693-2001.
All right, so that's quite amazing. All right, I'm just going to close that. And let's go back here. Yeah, so the film, so that's pretty interesting. So the film was also interestingly released on April 2nd, 1968, which is the same year as when the World Trade Center WTC construction began. And the difference, interestingly, between 1968 and 2001 is 33 years. So, and it's a pretty interesting number. So, April 2nd, 1968, Stanley Kubrick and Arthur C. Clarke's movie Space Odyssey is released. And then you have August 6, 1968, World Trade Center construction began then. All right, and here I just put a link to that article as well. Again, and this is all inside this one article I wrote on the Hive blockchain here, so you can go and see that article. But going further, and since year 1 is the start of the calendar, so that you don't start year 0, it means that 2001 is the start of the new millennium. Yeah, basically the second millennium. Again, millennium is 1,000 years. So again, you get that Millennium Hilton. And again, it's a new millennium, 2001, and it's literally a giant monolith there. So again, and there's a Twin Towers there, so that's quite fascinating stuff. So he also wrote a 1982 sequel titled 2010 Odyssey 2, which involved aliens telling humans not to land on Jupiter's moon called Europa. So Arthur C. Clarke, 2010's Odyssey 2, a daring romp through the solar system and a worthy successor to 2001. That's Carl Sagan giving a quote over there. So this is pretty, that's pretty fascinating. And then what's even more fascinating is fast forward to October 14th, 2024. Again, he wrote it 2010 Odyssey 2, but then October 4th, 2024, NASA launched the Europa Clipper space probe to study Europa, which they view as the best chance to find alien life, in other words, single-celled marine organisms, and it is scheduled to arrive on Europa in 2030. So again, a lot of stuff happening in 2030. And here's the NASA website. That's this one right here. This is nasa.gov, science.nasa.gov/Europa.Clipper. So you can see, read right here, why Europa up close, target arrives 2030. And it's a Europa Clipper is the first mission designed to conduct a detailed study of Jupiter's moon Europa, and there's scientific evidence that the ingredients for life may exist on Europa right now. The spacecraft will travel 1.8 billion miles, 2.9 billion kilometers to reach Jupiter in April 2030. It will orbit Jupiter and conduct 49 close flybys by Europa. And then here's some interesting read on this. So what will Europa Clipper do? Europa will try to determine if Jupiter's icy moon Europa currently has habitable conditions, and it will try to reach in April 2030. Again, that's fascinating stuff there. And the spacecraft carries 9 science instruments and a gravity experiment that uses the telecommunication system. All science instruments will operate simultaneously on every pass. Okay, here's an artist's rendition of this fascinating stuff. All right, and now going further on Arthur C. Clarke. So even more interestingly, Arthur C. Clarke had recorded interviews in 1966. I want to see if I can find these interviews. I got this from this article, from witnesses that saw a globular ray, in other words, ball lightning. And here I'm going to read some of that article there. So multiple witnesses to the natural phenomenon. So again, references Arthur C. Clarke recorded interviews with several people who saw the same globular ray at the small Scottish seaside resort of Crail in August 1966. So on the afternoon in question, Mrs. Elizabeth Radcliffe was walking home on a concrete path near the beach, and she said, I lifted my eyes and saw what I thought was a kind of light, and almost at the same instant it turned into a ball about the size of a tennis ball and a soccer ball. Then it passed over the grass and turned greenish, and then with great rapidity disappeared towards a cafe where it exploded. And thanks to the globular ray, there's a further an article, Hubler discovered that his true love is physics and the innermost secrets of the haunting world of nature. Too bad he didn't have any souvenirs left, like the round hole found after a storm in the glass of a broken window in the University of Edinburgh's meteorology department. As the glass was fused from the inside, the fact was attributed to a globular ray. So in other words, ball lightning. So again, there's some advanced physics going on right here. And also just for reference, here's an incredible video of ball lightning captured in Alberta, Canada last year in 2025. Yeah, just so we get that. Yeah, so 2025. So there's video there in Global News. Incredible video captured during Alberta storm. Could be rare ball lightning event. And apparently scientists can't explain that, but they believe it to be a rare phenomenon called ball lightning. So I already actually have this open already. So I already have this open. I'm going to play some of this.
What is it? It's going for a long time.
A ball of light hovers over a field.
It's like a fireball, but not really. It's the wrong color.
And this couple from Rich Valley, Alberta, was mesmerized.
After a rather vicious lightning strike, we saw the ball of fire kind of retain, 20 feet above the ground.
The cell phone video was captured an hour northwest of Edmonton by Ed and Melinda Party. It shows the ball of light for about 20 seconds before it disintegrates. They were under a tornado watch and experiencing a thunderstorm Wednesday evening when they saw this about a kilometer away from their home.
Yeah, it was moving horizontally above the ground. Incredibly bright, too.
It was very bright.
It was really bright.
Now, off in the distance, they see
All right,
something.
yeah. All right, that's fascinating stuff here. Let's go back here. Yeah, so there's a ball lightning. Zoom in again. That's again. Arthur C. Clarke is interviewing people that witnessed this, and he called it again. They were called globular rays back then. All right, yeah. Going further into this now. So lastly, Arthur C. Clarke. Actually, not lastly. Furthermore, because I have more stuff on it. Furthermore, Arthur C. Clarke also wrote the foreword on January 4th, 2004, Charles G. Bedette's 2002 book on cold fusion, again, which mainstream science says it's impossible, but again, it's obviously possible. It's obviously possible. So this book, Excess Heat, Why Cold Fusion Research Prevailed, Charles G. Bedette, forward, Sir Arthur C. Clarke, and then the author of 2001 Space Odyssey, introduction by David G. Nagel, a PhD research professor at the George Washington University. And so here's a part of the foreword right here. I'm going to read some of it because it's pretty interesting. So the contrary, the jury's still out. It is almost certainly the biggest scandal in the history of science. Charles Bedette, an MIT graduate with 30 years of engineering experience, has done a remarkable job in untangling and documenting the whole story of cold fusion. Excess Heat is not only a superb record of an extraordinary episode, but is also highly entertaining. The author does not hesitate to apportion blame where it is deserved, and there is enough to go around to satisfy everyone. I do not believe any unbiased reader will put down this book without feeling that something strange is happening at the fringes of physics. Although skeptics are still fond of intoning, quote, pathological science like a mantram, the wisest approach must surely be, quote, wait and see. Perhaps the most disappointing outcome would be if cold fusion turns out to be merely a laboratory curiosity of some theoretical interest, but of no practical importance. But this seems unlikely. Anything so novel would indicate a major breakthrough. The energy produced by the first uranium fission experiments was trivial, but everyone with an imagination knew what it would lead to. Of course, the most exciting possibility will be if these anomalous energy results can be scaled up. That could terminate the era of fossil fuels, end worries about pollution, and change the geopolitical structure of the world out of recognition. In 1973, when OPEC started to multiply the price of oil, I rashly predicted the age of cheap power is over. The age of free power is still 50 years ahead. Excess heat strengthens my hope that this may not be too far from the truth in the early millennium. So 50 there again, the year 2025. Hopefully he wants it. Year 2050. Actually, not 2050. It's starting from in 1973. He wrote. So at 50 years there, that's going to be the year 2023. So it's around basically. Now it's 2026. So he basically was hoping free energy is at least from that time. Excess heat strengthens my hope this may not be too far from the truth. Early in the new millennium, Arthur C. Clarke, that's Colombo, Sri Lanka, and that's his address for January 2000 OP 995. Interesting. And the fitting way to end this video on Kepler's 3 laws is by going over Arthur C. Clarke's own 3 laws, and I had no idea he had them. And the last of which is very profound. This again is Wikipedia on his 3 laws. So yes, what are the absolute odds that the video on Kepler's 3 laws, and then I somehow come across Arthur C. Clarke's 3 laws, and again, geosynchronous orbit is named after Arthur C. Clarke. So and then somehow that all ties in together. And also the last of his laws is very, very profound, especially with his foreword on cold fusion, his interviews with ball lightning, globular ray witnesses, and of course 2001 Space Odyssey. So that's and also 2010 Odyssey 2, which is the Europa moon and alien life and so on. That's pretty fascinating. So Law 1, when a distinguished but elderly science states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. That's a good law. The Law 2, the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And then his famous Law 3, any sufficiently advanced technology is indistinguishable from magic. All right, absolutely fascinating stuff. Anyways, and that is all for today. Again, there is some advanced technology right there, and right here creating this circular hole that's fused glass with it from the inside. So again, fascinating stuff from the inside. So that's what in the world's going on there. Anyways, that's all for today. Hopefully you enjoyed this epic video on Kepler's laws and Clarke's 3 laws. Right, and again, the notes for all of this will be in the link in the description below in both PDF and article format on the Hive blockchain. So anyways, thanks for watching, and yeah, I'm just going to scroll it back up, and I'll also be uploading each problem as a separate video, and then put it on the giant playlist, dissections playlist, and as well as a giant video as well. So again, put everything out there, and yeah, that's all for today, and thanks for watching, and stay tuned for another math easy solution.